Somewhere out there in space, floating alone in the cold, black nothing, is a star that's basically a giant diamond. No, this isn't science fiction. It's not a metaphor. It's not exaggerated. It's literally a crystallized chunk of carbon the size of a planet.
And it's real. Astronomers have actually found several of these. The most famous one is about 50 light years away in the constellation Centaurus. It's a white dwarf star, the collapsed core of a once living star, like our sun. But instead of being just a hot ball of gas, this one is mostly crystallized carbon and oxygen. In simpler terms, it's a diamond star. Its name is BPM through 7, Zone 93. The scientists nicknamed it something way more appropriate.
Lucy, after the Beatles song Lucy in the Sky with Diamonds. Here's how this cosmic gemstone exists. When a star like our sun runs out of hydrogen fuel, it expands into a red giant and then sheds its outer layers. What's left behind is the core, a white dwarf. These remnants are super dense and hot. Over billions of years, white dwarfs cool down, and the carbon inside them can begin to crystallize, just like diamonds do under high pressure on Earth.
Only this isn't a shiny little rock on a ring. It's a crystallized sphere, roughly the size of Earth and weighing more than the entire sun. Yes, you read that right.
Imagine something with the mass of the sun squeezed into the size of our planet and made of solid carbon crystal. That's Lucy. Its diamond core is estimated to be 10 billion trillion carats. That's a 1 followed by 34 zeros. If you could somehow mine it, spoiler, you can't, you'd be the richest person in the universe and then some. But this isn't the only diamond in the sky. In 2011, astronomers found something even weirder, a planet-sized diamond orbiting a pulsar. That's a neutron star, which is even denser than a white dwarf. This planet, about 5 times the size of Earth, is believed to be the carbon core of a dead star, and it orbits its pulsar once every 2 hours. That's right, a diamond planet whipping around a dead sun at breakneck speed. How do we even know these are made of diamond? We can't exactly fly out there and chip off a piece. It comes down to math, light, and physics.
Scientists measure the way white dwarfs vibrate as they cool, kind of like starquakes. These vibrations reveal details about the star's internal structure, just like how seismologists study earthquakes to learn about Earth's interior.
In Lucy's case, the data lined up with what you'd expect if a huge portion of the star had crystallized. And since white dwarfs are full of carbon and oxygen, the structure forming is essentially diamond. The process takes billions of years. Our own sun will eventually become a white dwarf in about 5 to 7 billion years. Then, after another few billion years, it will too cool and begin to crystallize. In other words, the future corpse of the sun will become a diamond.
Think about that. Our entire solar system, Earth, the moon, everything once orbited a yellow star. And someday, it'll orbit a crystallized jewel in space. No one will be around to see it. Earth might not even exist by then, but in the future, drifting alone in the darkness will be the diamond ghost of our sun. These stars shouldn't exist, at least not in the way we think about stars. We imagine them as burning gas balls, not silent, crystallized corpses shining with ancient heat. Lucy doesn't burn like our sun. It glows faintly with residual heat, slowly cooling over eons. One day it will go dark entirely, becoming a black dwarf. The final frozen state of a white dwarf. But the universe isn't old enough yet for any black dwarfs to exist. That stage is still trillions of years away. So right now,
These diamond stars just sit there, quiet, heavy, bright, and weird.
And here's another strange detail. Some white dwarfs pulse as they cool. This happens in a way that's eerily similar to how a bell rings when struck, except these bells are the size of planets, and their rings can be measured in light years.
The study of these stellar vibrations is called astroseismology, and it's how scientists confirmed that Lucy had started to crystallize. It's like space geology meets star music.
Astronomers believe that as many as 90% of all stars in the Milky Way will end their lives as white dwarfs. That means there could be billions of crystallized stars in our galaxy alone. Lucy isn't a rare fluke.
It's the start of a vast hidden population of diamond remnants waiting in the dark. And while we're talking numbers, if white dwarfs like Lucy become common enough, it's possible entire future civilizations might one day mine them.
Assuming technology exists to extract material from a corpse star with the gravity of a sun and the density of a nuclear bomb. Not likely, but not impossible.
One thing's for sure, the idea of giant diamonds casually floating through space isn't just a sci-fi image anymore. It's part of real astrophysics. They shouldn't exist, at least not if you asked a 17th century astronomer what stars are made of.
They'd tell you fire, gas, maybe divine light. Definitely not compressed carbon crystallizing into billion-carat gems. And yet, here they are. There's something poetic about it, too.
These stars that burned bright died quietly and now sit frozen as diamonds, like a cosmic gravestone made of light and pressure and time. It sounds fake. It sounds like the setup for a fantasy novel, but the diamond stars are real. In space, things are supposed to follow certain rules. Big, bright stars burn hot. The planets around them are cooler. That's just how heat works, right? Well, not always. There's a planet out there that's hotter than the very star it orbits. Let that sink in. A planet hotter than a star. It sounds completely backwards, like finding ice cubes that melt fire. But it's real. It's called Kelt 9b. And it breaks every expectation we have for how a planet should behave. Let's start with the basics. Kelt 9b is a gas giant like Jupiter, but that's where the similarities end. It orbits its star so closely, once every 1.5 Earth days, that it's practically skimming the surface. The star, Kelt 9, is already no slouch.
It's a Blu-ray type star, more massive and hotter than our sun. But the planet is so close that it's blasted with over 4,000 times the radiation Earth receives from the sun. The result? The planet's day-side temperature hits 4,300 degrees, hotter than many small stars.
That's not a typo. Kelt 9b is hotter than red dwarfs, which are fully functional stars. It's hotter than the surface of the sun in places, and it's not even made of fire or fusion. It's just a poor planet being scorched by proximity.
The heat is so intense that molecules can't exist on the day side. Not clouds, not water, not even hydrogen molecules. The atoms themselves get ripped apart. The atmosphere becomes a churning soup of individual atoms. Iron, titanium, hydrogen, all boiling in the heat.
But the weirdness doesn't stop there. Kelt 9b is also evaporating. Its atmosphere is literally being blasted off into space by ultraviolet radiation. Think of it like a comet trailing gas as it goes, except the gas is hydrogen and the trail is massive.
Some models suggest it's losing millions of tons of material every second. Over time, it might completely vanish, boil down to nothing. And it's tidally locked. That means one side of the planet always faces the star. Permanent day.
The other side is an endless night.
but the temperatures are so extreme that even the night side is blisteringly hot, hot enough to melt metals. Scientists estimate the cool side is still over 2,000.
The heat doesn't just affect the atmosphere, it affects the shape. Due to the intense radiation and gravitational stretching, Kelt 9b isn't spherical. It's distorted, more like an egg. The gravity from the star pulls the planet into an oblong shape.
It's being stretched and twisted just by existing that close. It shouldn't be able to hold itself together at all. And yet, somehow it does. Kelt 9b orbits so close to its star that it may eventually spiral in and be destroyed. That's the likely ending. Burned, boiled, and broken apart until it's nothing but scattered gas. It's already circling dangerously close to what scientists call the rush limit, the point where the tidal forces from the star would tear the planet apart.
And get this, it orbits poles up. Planet's orbit is tilted 90 degrees compared to the star's equator. This isn't just weird, it's rare. Most planets orbit around the equators of their stars like flat, spinning plates.
But Kelt 9b plunges headfirst across the star's poles. It's not just being baked, it's being flung sideways. Why? We're not sure. Maybe it was gravitationally kicked into that orbit by another planet long ago. Maybe the star itself tilted after forming.
Whatever happened, the planet is now trapped in a gravitational and thermal torture chamber, endlessly circling, cooking, and eroding. From Earth, we can't see it directly, but we detect it through transit photometry and spectral analysis.
As Kelt 9b passes in front of its star, we measure the tiny dimming in light. More importantly, we analyze the starlight filtering through the planet's atmosphere. That's how we know what it's made of, or rather, what's left of it.
Using this method, scientists have detected vaporized iron, titanium, sodium, calcium, and even hydrogen tails extending far into space. The atmosphere is so puffy and inflated by heat that it nearly touches the star. Kelt 9b shouldn't exist. Not this close, not this hot, not orbiting this way. It pushes the boundaries of what we consider a planet. In fact, it's making scientists reconsider how we define planets at all.
Because most gas giants form far from their stars in the cold, where gas can condense and clump together. To get as close as Kelt 9b, it had to migrate inward after forming.
That means this planet probably traveled a vast distance, brushing past other objects, surviving gravitational chaos, only to end up on a death spiral. And it still hasn't died yet. It's a cosmic daredevil. A planet that flies too close to the flame and somehow holds on. In a universe that loves rules, Kelt 9b is an exception. Too hot, too close, too unstable, too tilted, and somehow completely real.
If there's one thing we thought we understood about galaxies, it's that they need dark matter to hold together. That invisible stuff, mysterious, undetectable by light, is supposed to make up the scaffolding of the universe. Without it, galaxies would fly apart.
Stars wouldn't stay in orbit. Gravity alone from visible matter just isn't enough. So when astronomers discovered a galaxy with no dark matter at all, the entire astrophysics community did a double take. This galaxy is called NGC 1052 DF2, or just DF2 for short.
From a distance, it looks faint, wispy, unremarkable, but it's one of the strangest things we've ever found in the cosmos. It shouldn't exist, not by the rules we've been following for decades.
DF2 is an ultra-diffuse galaxy located about 65 million light-years away. It's roughly the same size as the Milky Way in diameter, but it has the 200th the number of stars.
Imagine a ghost version of our galaxy. Same size, barely any substance.
Like someone blew up a balloon and forgot to put anything inside. At first, scientists thought this was just another strange, faint galaxy. But then they studied its star clusters, tightly packed groups of stars that orbit around the galaxy. The key was measuring how fast those clusters were moving. If there was a lot of mass hidden in the galaxy, like say dark matter, then the clusters would be moving fast, pulled in tight by gravity. But they weren't.
They were moving slowly, way too slowly for a galaxy of that size, unless it had almost no dark matter at all. In other words, the stars were held together only by the visible matter.
No extra gravity, no dark matter halo, just plain old baryonic matter, what we can see. That was unprecedented. Every galaxy we've ever studied seems to have dark matter as a fundamental component. It's what keeps stars from flying off in the deep space.
Without it, galaxies simply shouldn't form, at least not like this. So DF2R immediately broke the rules. Naturally, there was skepticism. Maybe the measurements were off. Maybe the galaxy was closer than we thought, which would change the calculations. Maybe we were missing something.
But then in 2019, scientists found another galaxy with the same properties. NGC 1052 DF4, a twin to DF2, just a little further away. Same ghostly structure, same lack of dark matter. It wasn't a fluke.
These galaxies truly seem to exist without dark matter, which is a huge problem or maybe an opportunity for astrophysics. Because up until this point, dark matter was non-negotiable. Every galaxy needed it. We couldn't detect it directly, but we saw its gravitational effects everywhere.
Galaxies rotating faster than they should, light bending around invisible mass, clusters held together by unseen glue. So how does DF2 stay together? Here's the thing, it barely does. The stars in DF2 are spread out and dim. It's a translucent wisp of a galaxy.
Fragile, tenuous, almost falling apart. It's like someone accidentally assembled the galaxy and forgot the glue. And yet it's been floating around in space for billions of years. One theory is that DF2 formed in a violent interaction.
Maybe a larger galaxy stripped away its dark matter, leaving just the bare, luminous core behind. Another theory suggests that it formed in an unusual environment where dark matter was never dense to begin with, like building a sandcastle in the shallows instead of on the beach.
And then there's the truly wild possibility. What if this is telling us dark matter isn't universal? That maybe not every galaxy needs it? That the rules aren't as fixed as we thought?
It could even support alternative gravity theories, ideas like MOND, modified Newtonian dynamics, which suggest gravity behaves differently at galactic scales. If galaxies can form without dark matter, maybe we need to rethink how gravity actually works in deep space.
But before we rewrite physics textbooks, here's a reality check. DF2 is weird, but it's not the only thing out there. We've also discovered galaxies with way too much dark matter. Galaxies where the stars are moving impassably fast for the amount of visible mass.
That means some galaxies hoard dark matter like dragons guarding treasure, while others, like DF2, have almost none. What's going on? Are there two types of galaxies? One family rich in dark matter, one nearly empty.
Or are galaxies like DF2 just the cosmic equivalent of a biological mutation, rare outliers that reveal hidden truths? It's too early to say for sure.
But the fact that multiple galaxies now appear to lack dark matter is enough to challenge the one-size-fits-all model we've been using. And just to add another twist, DF2 is not invisible. You can actually see it with strong enough telescopes.
Its low surface brightness makes it faint, but not impossible to observe. It's a ghost you can photograph. Also, its globular clusters, the ones that reveal their lack of mass, are unusually bright. That's part of what made the discovery possible.
They're like little cosmic beacons orbiting the ghost of a galaxy. And yes, scientists doubled everything. Checked. Distances, emotions, light measurements. The conclusion kept holding up. This galaxy really doesn't need dark matter to explain its structure. That doesn't mean dark matter doesn't exist.
It almost certainly does. There's too much evidence for it across the universe. But galaxies like DF2 suggest there are exceptions to the rule. And in science, exceptions are gold. They force us to ask questions better. They expose cracks in our assumptions.
They remind us that the universe doesn't owe us simplicity. Just because we built a model doesn't mean the cosmos will play along. DF2, the galaxy with no dark matter, shouldn't exist.
And yet it floats, barely held together, defying the invisible forces that shape the rest of the universe, shining softly like a warning. Not everything fits the mold. This one flips expectations on their head.
You'd think that in a planet-moon relationship, the planet would be the dominant one. Bigger, heavier, more massive. The one with the magnetic field, the atmosphere, the power. The moon, just a rock that tags along. But space doesn't care what makes sense.
Because out near Saturn, there's a moon that has a thick, active, hazy atmosphere, while the planet it orbits doesn't have one at all. The moon is Titan. The planet, or rather the object, is Saturn's other moon, Rhea, or Dione, or Tethys.
Pick almost any of Saturn's moons, and you'll see the pattern. Titan is the only one with a full atmosphere. Not thin vapor, not a trace. A real dense pressure-bearing atmosphere. In fact, Titan's atmosphere is denser than Earth's. But it gets weirder.
Titan's atmosphere isn't just a fluke of gas. It has weather, clouds, wind, rain. It forms storms and shapes the landscape. But what it rains isn't water. It rains liquid methane. Titan is like a frozen Earth, reimagined with completely different ingredients.
Seas, lakes, rivers, but made of hydrocarbons instead of H2O. And yet it's just a moon. Meanwhile, Mercury, a full-blown planet with nearly twice Titan's diameter, has almost no atmosphere at all.
Same for our moon. Same for Pluto, which only has a temporary thin haze when it's near the sun. Even Mars, a world 100 times more massive than Titan, has an atmosphere so thin you couldn't survive a second without a pressure suit.
So why does Titan, of all things, have the atmosphere? To answer that, we need to talk about chemistry, cold, and time. First, Titan is incredibly far from the Sun, over 1.4 billion kilometers away.
The surface temperature is around 179 degrees Celsius, cold enough to make water hard as rock. But that extreme cold is the key. It slows down molecules. Gas particles move sluggishly.
So, even though Titan has low gravity, only about 14% of Earth's, it can still hold on to light gases like methane and nitrogen because they're not moving fast enough to escape.
Second, Titan's atmosphere is mostly nitrogen, just like Earth's, but it also has a few percent methane, which makes all the difference. Methane breaks down under sunlight, forming complex organic molecules. These molecules drift down through Titan's air and create a thick orange haze.
That haze blocks sunlight, traps heat, and makes Titan look like a blurry orange ball from space. It's like Earth small, but planet-wide and permanent. Now, why don't other moons have this? Some of it comes down to size.
Titan is the second largest moon in the solar system, just a hair smaller than Jupiter's Ganymede. It's even bigger than Mercury, so it's not your average moon. It has enough mass to hold an atmosphere if the conditions are right.
And on Titan, they are. But here's the twist. Even Saturn, the gas giant Titan orbits, doesn't have a true solid surface. It's mostly hydrogen and helium, a giant ball of gas with a core buried deep inside.
So, in a sense, Titan has something Saturn doesn't. A real surface you could stand on and an atmosphere that could shape that surface. And shape it does. Titan has dunes, ridges, valleys, storms. Methane rain carves river channels into the icy crust.
Radar images from the Cassini mission showed liquid lakes at the poles, some bigger than the Great Lakes on Earth. There's even a methane cycle: clouds, rain, runoff, evaporation, like Earth's water cycle, but made of flammable gas. Let's just pause on that.
This is a moon with seasons, storms, weather, and liquid on the surface. Not a planet, not a mini Earth, a moon. Its atmosphere is thick enough to fly in. Seriously, if you flapped your arms while wearing wings, you might get airborne.
The dense air and low gravity make Titan the easiest place in the solar system to fly. That's part of why NASA is sending a drone there. The mission, called Dragonfly, is set to launch in 2028.
It will fly across Titan's surface, sampling organic molecules, testing chemistry, and searching for the building blocks of life. It'll be the first time we fly an aircraft on another moon. And Titan's thick atmosphere is what makes that possible.
Now, compare that to most moons. Dry, dead, airless, no erosion, no rain, just ancient craters and dust. They look the same as they did 1 billion years ago. Titan, it's active, changing, alive in a geological sense. It shouldn't be.
It defies our expectations of what moons are supposed to be. It's got more in common with early Earth than with its own planetary siblings. If you replace the methane with water and raise the temperature by a couple hundred degrees, it might feel eerily familiar.
And scientists think that beneath Titan's icy shell, there may be a liquid water ocean heated by tidal flexing from Saturn's gravity. That means Titan might have 2 layers of liquid. One on the surface made of methane, and another deep below made of water and ammonia. 2 alien oceans on one moon with the potential for life in both. It's not just an oddity, it's a prime candidate for astrobiology.
If life can form in hydrocarbons, or if there's chemistry happening in that hidden ocean, Titan might be the first place we found non-Earth-based life. And yet again, it's a moon. Even weirder, it has this atmosphere and no magnetic field to protect it.
Solar wind should have stripped it long ago, but it hasn't. The haze may help. Saturn's magnetic field may help. Or maybe Titan is just leaking methane from inside fast enough to replace what's lost.
Whatever the case, Titan holds onto its air, while other bodies, including much larger ones, have none. This moon shouldn't have an atmosphere. It shouldn't have lakes. It shouldn't have clouds, rain, dunes, or seasons.
It shouldn't be this Earth-like or this alien all at once, but it is, and it's not just weird, it's scientifically invaluable. Titan shows us that life-supporting environments don't have to exist on planets.
Sometimes the most Earth-like world in the solar system isn't a planet at all. It's a moon with an atmosphere orbiting a gas giant, doing things no moon should be able to do. There are things in space that seem impossible, even on paper.
And this might be one of the strangest, a star that got hit by a supernova and survived.
Yes, not metaphorically, not figuratively, a real supernova. An actual star exploded with the force of several octillion nuclear bombs,
And somehow another star that was right next to it just kept going. It should have been vaporized, annihilated, turned into cosmic shrapnel. But it wasn't. It lived. And it's out there right now, drifting away like nothing happened. Let's unpack how insane this is.
This stellar survivor is called LP40365. It's located about 2,000 light-years from Earth. At first glance, it doesn't look particularly special. It's a white dwarf, a small, dense, stellar corpse glowing faintly with residual heat.
But when scientists looked closer, the weirdness started piling up fast. First red flag, it's moving way too fast. This little white dwarf is blazing out of the galaxy at over 850 kilometers per second. It's nearly 2 million miles per hour.
It's one of the fastest stars ever observed, fast enough to escape the Milky Way entirely. In cosmic terms, it's making a clean getaway. That alone was strange. But then they looked at the composition, and things got even weirder.
Normal white dwarfs are made mostly of carbon and oxygen, but LP40365 is full of heavy metals like manganese, iron, and nickel, elements that usually form in supernova explosions. It's chemically scorched like it went through a nuclear furnace.
So scientists put the puzzle together. This wasn't just any old white dwarf. It was half of a binary system, a pair of stars orbiting each other closely. One of them exploded in a type of supernova, a catastrophic detonation that usually wipes out everything nearby.
But instead of getting obliterated, LP40365 was somehow flung away from the blast. Not just flung, survived the explosion, changed its chemistry, and kept going.
It's like standing next to a live volcano that erupts and blows the entire mountain away, and you just catch a gust of wind and land on your feet. That shouldn't happen, ever. Yet LP43646 is proof that it can.
This star isn't just fast, it's also stripped and damaged. It's missing hydrogen, missing helium. The outer layers were burned off, likely by the blast. What's left is a dense, charred core, full of heavy elements and radioactive scars.
It's the astronomical equivalent of a burn victim, disfigured, traumatized, but alive. Even more bizarre, this survivor star doesn't fit the normal white dwarf profile. It's less massive, hotter, and more inflated than it should be. In a sense, it's like a zombie star.
Something that died, kind of, but didn't stay dead. And here's a plot twist. LP4365 may not have just survived a supernova, it might have been part of the explosion itself.
Some models suggest that in rare cases, two white dwarfs can spiral together in a binary system. When they collide, the more massive one can explode, while the smaller one absorbs part of the blast, then ricochets away. Half destroyed, half ignited, and fully ejected.
That's the working theory for LP40365. It was part of a failed supernova, not just a victim, participant. It's so weird that scientists have created a new category, partially burned runaway stars, and LP4365 might just be the first known example.
Let's get technical for a second. In a classic type Ia supernova, a white dwarf accretes matter from a companion star until it reaches critical mass, ignites carbon fusion, and detonates in a thermonuclear explosion. The blast vaporizes the white dwarf and anything nearby. But if the explosion is off-center, or if two dwarfs merge imperfectly, the detonation can be asymmetrical. One half explodes, the other gets flung, burned, but intact. And that might be how you end up with a runaway zombie star like LP4365.
Now, this star is on a one-way trip.
Its trajectory means it's headed out of the Milky Way entirely into intergalactic space. In a few 100 million years, it'll be beyond the reach of even our most powerful telescopes.
Alone, exiled, and forever drifting in silence. No star-forming region, no planets, no sunlight, just a burned remnant with a radioactive past floating through the void. And here's the final twist. It's not alone. Astronomers have since found others like it.
Stars with similar velocities, strange compositions, and messed up atmospheres. There may be a whole population of these supernova survivors, ghosts of past explosions shot from their systems at insane speeds, now scattered across the galaxy like war veterans with scars and stories.
They shouldn't exist. Everything we know about supernovae says total destruction. No survivors, no close calls, no half-burned stowaways. But LP 4365 is real. It's proof that the cosmos doesn't always follow its own rules, and that sometimes a star can stare into the heart of an explosion and walk away.
If you think the weather on Earth is bad, wait until you meet HD 89733b, a planet where it literally rains glass. And not gently, it rains glass sideways at speeds of over 5,400 miles per hour. You read that right.
On this alien world, the skies are deep blue, the winds are supersonic, and the rain will slice you to pieces. If Dante wrote Inferno for planets, this would be one of the deeper circles. Let's start with the basics.
HD 89333b is a hot Jupiter, a gas giant about the size of Jupiter but much, much closer to its star. It orbits months every 2.2 Earth days, which means it's insanely close to its host star.
About 30 times closer than Earth is to the Sun, so close that its atmosphere is superheated to over 1,000 degrees Celsius. The planet is tidally locked, so one side always faces the star, endless day, while the other side lives in perpetual night.
The temperature difference between the two sides creates violent pressure gradients, and that leads to winds unlike anything we see on Earth. These winds scream across the planet at more than 2 kilometers per second. That's 7 times the speed of sound.
That's fast enough to blow apart clouds, erode molecules, and shred any solid surface, if it had one. But here's the part that makes it truly alien. The planet's atmosphere contains silicate particles, tiny glass-like grains suspended in the high-altitude clouds.
At such high temperatures, these silicates can condense, forming droplets of molten glass. Then gravity pulls them down. Except they don't fall straight. Because the winds are so fast, the droplets travel sideways, slashing across the atmosphere like shrapnel.
Imagine standing in a hurricane, where instead of water, the wind throws melted glass at your face, sideways, at hypersonic speeds. That's HD 899733b. There's no weather warning system for that. And it gets weirder.
The planet's blue color, captured in visible light by the Hubble Space Telescope, comes not from oceans, there are none, but from scattering in its atmosphere.
Just like Earth's sky appears blue because of scattering, this planet's blue comes from tiny glass particles in high-altitude haze reflecting blue light. So from far away, it looks kind of beautiful, tranquil, Earth-like, a calm blue dot.
But up close, it's a stormy, shattering hellscape. And that's part of what makes HD 9733b so unsettling. It looks inviting, almost familiar, and then reveals itself to be one of the most hostile places imaginable.
This planet's wind speeds are not just fast, they're some of the fastest in the known universe. For comparison,
The fastest winds on Earth, inside tornadoes, can hit 300 miles per hour. Neptune's fastest winds top out at around 1,300 miles per hour.
HD 89733b dwarfs both, with sustained speeds nearly 5 times faster than a bullet. Even the sound of the wind would be unearthly if sound could travel in the thinning upper atmosphere. But it likely couldn't because the planet is gas.
There's no surface to land on, no place to stand, just layers of heated, howling, glass-filled air wrapping endlessly around the planet's body. And here's another twist. Those clouds of silicate might change color over time, depending on altitude and composition.
Some models suggest the planet's upper haze could fluctuate between gray, copper, or even fiery red, depending on chemical reactions and how deep we're seeing into the layers. But we're just guessing. All of this is inferred from light.
We detect this insanity not by visiting the planet, but by studying how its star's light passes through the atmosphere when the planet crosses in front of it. This is called transit spectroscopy. We use it to read the fingerprints of elements in the atmosphere.
Sodium, methane, silicates, all hidden in the light curve. That's how we know about the glass. We've never seen the glass full, never watched it scatter in a storm.
But the spectral data matches what you'd expect if small glass grains were forming and being redistributed at high speed. So the glass storm isn't science fiction, it's science in progress. And the planet isn't alone. There may be many exoplanets like this.
Gas giants with high-temperature silicate weather rain in corundum, iron, or even rubies and sapphires under the right conditions. In the exoplanet weather forecast, rocks falling from the sky is normal, but HD 189733b is still one of the most extreme. It's close, it's blue,
It's beautiful, and it's utterly lethal. It shouldn't exist, at least not in any planetary model we had 50 years ago. We thought gas giants belonged far from stars, cold and slow like Jupiter and Saturn, not scorched, storm-tossed, and violently irradiated.
HD 89733b is the poster child for hot Jupiters and for what happens when the laws of planetary formation get rewritten by data. And it's still out there, shining bright and shredding itself sideways in a rain of flying glass.
A planet that looks calm and tears itself apart one storm at a time. Some things in space are just hard to believe. But this one doesn't just sound fake. It breaks reality wide open. The universe is being pulled apart, not slowly, not passively.
It's accelerating. Galaxies are moving away from each other faster and faster, as if some hidden force is pushing the cosmos outward like it's trying to rip itself in half. We call that mysterious force dark energy.
And we have no idea what it actually is. None. It makes up nearly 70% of the known universe. It controls the fate of everything, and we discovered it by accident. Let's rewind.
For most of human history, we assumed the universe was either static or slowing down. After all, gravity pulls things together. If the Big Bang hurled matter outward, gravity should have been putting on the brakes ever since. But in the 1990s, two independent teams of astronomers were studying Type Ia supernova, exploding stars that are so bright we can use them as cosmic mile markers.
They were measuring how fast galaxies were receding at different distances, expecting to see the expansion slowing down over time. What they found instead shocked everyone. The distant supernovae were dimmer than expected, meaning they were farther away than they should be.
That only made sense if the expansion of the universe wasn't slowing down, it was speeding up. Something was pushing space apart with more force than gravity could contain. This wasn't a minor correction. It was a complete rewrite of cosmology.
Suddenly, the biggest, most dominant component of the universe wasn't matter, stars, or black holes. It was a repulsive, invisible pressure spread across all of space, and we had no name for it. So we called it what it is: dark energy.
Dark because we can't see it. Energy because it acts like a force, a placeholder term for something we don't understand or at all. Here's what we do know. Dark energy is everywhere, but it's not tied to matter like gravity. It's not a particle. It doesn't clump. It acts uniformly across space. It seems to have constant density, meaning as space expands, dark energy just keeps filling it in, maintaining its pressure. In simple terms, the more space you have, the more dark energy there is.
And the more dark energy there is, the faster space expands. It's a cosmic feedback loop. It's not just pulling galaxies apart, it's pushing space itself wider, even in the most distant, empty regions of the universe.
And the force is so dominant that everything else is losing the fight. Gravity can still pull matter into stars, galaxies, and clusters, but at the larger scales, millions, billions of light years, dark energy wins.
Eventually, if it keeps accelerating, it could push galaxies so far apart that light from other galaxies can't reach us anymore. In that future, the night sky might go dark.
We'd be left in an island universe surrounded by black nothing, with no visible clue that other galaxies ever existed. It sounds dramatic, but the evidence is piling up. We've confirmed cosmic acceleration through multiple lines of data.
Supernovae redshifts, cosmic microwave background measurements, baryon acoustic oscillations, large-scale galaxy surveys, all of it points to the same conclusion. Something is pushing space apart, and it's doing it faster and faster. So what could it be?
There are a few theories, all of them strange. 1. Cosmological constant L. Einstein originally added this term to his equations to make the universe static. Later he called it his biggest mistake. But maybe it wasn't.
A cosmological constant would represent a built-in energy of empty space. Quantum fluctuations in the vacuum, the jitter of nothingness, might provide a small, constant pressure. Problem is, theoretical calculations of this energy are off by 120 orders of magnitude.
Literally the worst prediction in physics. 2. Quintessence. This is the idea that dark energy is dynamic, not constant. Maybe a new field that changes over time. It could decay. It can increase. It could interact with gravity.
No one has found it, but it opens the door to complex behavior, including dangerous ones. 3. Modified gravity. Maybe we're wrong about how gravity works at Lord Stales.
General relativity has passed every test locally, but what if it breaks down over billions of light years? Some versions of this theory suggest gravity itself has a built-in repulsive component we haven't fully modeled yet. 4. The Big Rip. If dark energy keeps accelerating and its strength increases over time, it could eventually tear the entire universe apart. First galaxies, then stars, then planets, then atoms, until even space and time are destroyed in a final catastrophic unraveling.
This is just one possible endgame, but it's a terrifying one. The point is, we don't know, and yet we've confirmed its existence through precision measurements. We know what it's doing, we just have no clue why. It's not the only dark force at work either. Combine dark energy with dark matter, another invisible, unknown component of the cosmos, and we don't understand 95% of the universe. Only 5% of the cosmos is made of regular matter. Stars, gas, planets, people.
The rest is made of two things we can't detect directly, can't produce in a lab, and can't fully explain. Think about that. The thing controlling the fate of the entire universe, how fast it expands, how big it gets, how long it lasts, is something we didn't even know existed until the late 20th century.
A force that's silent, invisible, constant, and utterly inescapable. It doesn't burn, doesn't emit light, doesn't interact with matter, but it's winning. Dark energy shouldn't exist because we can't explain how it exists. Yet, the galaxies are flying away.
The void is getting wider. The universe is expanding faster today than it was a billion years ago, and there is no sign of it slowing down. If planets raining glass or stars surviving supernovae sound wild, this next one takes things to absurd extremes.
Imagine something the size of a city with more mass than our sun, spinning faster than the blades of a blender. Not once every minute, not even every second. Try 700 times per second. This is real. It's not science fiction.
It's a neutron star, and it's spinning so fast it's basically one giant cosmic buzzsaw. Its name? PSR J174824. Catchy, right? But behind that awkward string of numbers is a record-breaking fact. This is the fastest spinning known neutron star in the universe. It rotates at an insane 43,000 revolutions per minute. That's faster than a dentist drill, faster than any engine. And it's doing this with the mass of the sun packed into a ball just 20 kilometers wide. Let that sink in.
This object is so dense, a single teaspoon of its material would weigh about 1 billion tons. It's made almost entirely of neutrons, jammed so tightly that atoms can't exist in their normal form. Electrons and protons have fused.
What's left is pure nuclear matter, a solid ball of dead star, spinning faster than anything else in the cosmos. So how does something like this exist? It starts with a star dying.
A massive star runs out of fuel, explodes in a supernova, and its core collapses under gravity. If it's not big enough to become a black hole, it becomes a neutron star instead, an ultra-dense remnant that spins as a consequence of angular momentum.
Like an ice skater pulling their arms in, the collapsing core spins faster as it shrinks. Some neutron stars are born spinning fast, but millisecond pulsars like PSR JON 74 plus TU-DN6 are in a league of their own.
They weren't just born fast, they were spun up over time. How? By stealing. These neutron stars often orbit a companion star. Over millions of years, they pull gas off that companion, forming a swirling disk of material that rains onto the neutron star's surface. This process transfers angular momentum, accelerating the spin. The more matter it steals, the faster it spins, until it's whirling at speeds that almost rip it apart. PSR JC 2748 to 46 AD reached that limit. It spins so fast that if it were going even 1 rotation per second faster, it might tear itself apart from centrifugal force. It's right on the edge of rotational breakup, the maximum theoretical speed a neutron star can spin without flying to pieces.
And it's holding together barely. It's also a pulsar,
a special kind of neutron star that beams radiation from its magnetic poles. As it spins, those beams sweep across space like the light from a lighthouse.
From Earth, we detect rapid pulses of radio waves, hundreds per second, so precise that they rival atomic clocks. That's not a metaphor. Millisecond pulses are so consistent that some researchers are using them as galactic GPS systems.
The network of these stars could serve as navigational markers for deep space travel. It's like building a map using the spinning corpses of dead suns. Now, PSR J. Satan, 41048 and 2468, lives in a globular cluster.
A dense, ancient group of stars called Terrazan 5, located about 18,000 light-years away in the constellation Sagittarius. These clusters are crowded, chaotic, and packed with stars, perfect breeding grounds for weird stellar interactions, collisions, captures, mergers.
So it's not surprising that something as bizarre as a hypermagatar neutron star would live there. And here's where things get stranger. Despite spinning faster than anything else known, PSRJ 174824046AD isn't tearing apart its environment. It's just spinning quietly, invisibly.
Its surface speed is about a quarter the speed of light, and yet it's perfectly stable. We can't see it with our eyes. It doesn't shine like a regular star, but we can detect its pulses.
Tiny blips of radio waves arriving with a rhythm so fast and consistent that it's almost hypnotic. Tick, 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 716 times per second. You can actually listen to these pulses converted to audio. Tuk, 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 tuk.
And when you do, you're hearing the heartbeat of a dead star, ticking faster than any drummer's hands could ever move. This object shouldn't exist, not without tearing itself to shreds. But it does, because neutron stars cheat physics just a little. Their gravity is so intense, and their matter so tightly packed, that they can withstand internal stresses that would obliterate anything else. No Earth-based object could spin that fast and stay intact.
But a neutron star is more steel than star, held together by nuclear forces that are almost unfathomable. And here's one final mind-bender. We're not even sure 700 spins per second is the upper limit.
There might be neutron stars spinning even faster, but we haven't detected them yet. They could be oriented in such a way that their beams never point towards us, or they might emit in wavelengths we haven't noticed.
In other words, the fastest object in the known universe might still be out there, spinning faster than anything we can imagine, and we just haven't caught it in any act.
So, next time you think about how fast something can go, a jet, a race car, a bullet, remember this. There's a dead star 18,000 light-years away that could outspin all of them in less than the blink of an eye.
When we think of space, we think of cold. The kind of cold that kills electronics, freezes fuel, rips heat from your body in seconds. Deep space, the vacuum between stars, is a place where temperatures hover just above absolute zero.
26 sols for speed, or 2.7 Kelvin. That's cosmic background temperature, the leftover glow of the Big Bang, the coldest anything can get without completely stopping. Except something in space is even colder than that, significantly colder. We're talking 1 Kelvin.
Not deep in intergalactic space, not in a black hole shadow, but inside a nebula, glowing with infrared light, nestled in our very own galaxy. It's called the Boomerang Nebula, and it might just be the coldest natural place in the entire universe. Let's rewind.
The Boomerang Nebula is about 5,000 light-years away in the constellation Centaurus. From afar, it looks like a faint, ghostly hourglass, a gentle puff of stardust glowing faintly against the void.
But what's happening inside is anything but gentle.
At its heart is a dying star, or rather a red giant shedding its outer layers in a violent stellar wind. That's not unusual. Lots of stars do this in their final phases, but this one is doing it so fast and with such intensity that it's creating a kind of cosmic deep. Here's how. As the star blasts its gas outward at speeds over 160,000 kilometers per hour, the material expands rapidly. And when gas expands in a vacuum, without friction, without heat, it cools fast.
This is the same principle behind how your air conditioner works, but on a scale that dwarfs human machines. The gas around the Boomerang Nebula is expanding so quickly that it cools below the temperature of the cosmic microwave background.
That's colder than the ambient temperature of space itself. Let's pause on that. The universe has a baseline temperature, a floor, set by the leftover radiation from the Big Bang. It permeates everything.
Even in the deepest, darkest regions, this faint hum of microwave energy keeps things from reaching absolute zero. But the Boomerang Nebula doesn't care about that rule.
Its expanding gas cooled itself so aggressively that it dips a full degree lower to about 1 Kelvin, or 272.15 Celsius. That's as close to absolute zero as nature has ever gotten. And remember, this isn't a lab experiment. This is a real place in the universe right now. No insulation, no liquid nitrogen, just stellar physics doing what it does for best, blowing our minds. Astronomers discovered this anomaly in the 1990s using microwave telescopes. They were scanning the sky, looking for interesting features when they noticed a dark spot. Not because it was absorbing light, but because it was emitting less radiation than the background, less than the Big Bang itself.
At first, it looked like a glitch, but further observation confirmed it. This wasn't an absence of material. It was a supercooled outflow, colder than anything ever observed in nature. And it's beautiful.
High-resolution images from the Hubble Space Telescope show twin lobes of gas expanding outward like wings. The inner regions are dense, dark, and cold. The outer layers catch light from the central star, glowing faintly in the infrared.
The whole structure resembles a butterfly or a boomerang, hence the name. But what makes it truly extraordinary isn't the shape, it's the physics. To cool gas this much, the outflow has to be incredibly efficient. No collisions, no radiation, just rapid, unimpeded expansion into emptiness. The Boomerang Nebula is pulling off a thermodynamic magic trick, using motion alone to beat the cosmic thermostat. And it won't last. The star at the center is evolving.
Eventually, it will become a white dwarf. Its stellar wings will slow. The outflow will stop. The nebula will be warm. In a few thousand years, a blink in astronomical terms, this record-breaking cold pocket will vanish.
But for now, it's there. Real. Measurable. A patch of the universe where the laws of physics have produced a place colder than the background of the cosmos. And that changes how we think about the universe.
We used to believe that the coldest anything could be naturally was the 2.7 K of the cosmic microwave background. After all, that's the baseline temperature of everything, the wallpaper of the universe. But the Boomerang Nebula doesn't care about our assumptions. It's colder.
Not by much, but enough to break the rules. Enough to remind us that even the edges of thermodynamics can be tested in deep space. Enough to make astronomers go, wait, what?
So, the next time someone tells you space is cold, remember it can get colder. A lonely dying star in the Centaurus arm is manufacturing cold, chilling gas to levels even the Big Bang can't reach. It shouldn't be possible, but it is. and it's still out there, floating like a frosted ghost in the night sky. There are black holes, and then there's TON 618. This one isn't just big, it's impossibly big. So big it shouldn't exist.
Not at the time it formed, not in the place it's located, not under any of the models we currently use to explain how black holes grow. But it's real, and it's out there.
Tipping the cosmic scales at over 66 billion times the mass of the Sun. Let that number settle. That's 66 billion solar masses, more than the mass of the entire Milky Way, packed into a single compact object with the gravitational pull so strong it could swallow our entire solar system in one gulp and not even burp.
This is TON 618, a quasar, meaning it's a supermassive black hole at the center of a galaxy actively feeding. It devours matter at such a ferocious rate that it releases an enormous amount of energy, outshining every star in its host galaxy combined.
In fact, TON 618 is one of the brightest objects in the known universe, even though it's 10.4 billion light-years away. That's not a typo.
It's so far that the light we see now left the quasar when the universe was only about 3 billion years old. And that's the problem. It's too early.
There shouldn't have been enough time in the early universe for a black hole to grow this huge. Not unless it broke every rule we know about how black holes evolve. Let's talk about that. We know black holes form when stars collapse.
These stellar mass black holes start small, a few solar masses. Over time, they can grow by accreting gas or merging with other black holes. But growth is slow.
It's limited by the Eddington limit, a point where the radiation pressure from infalling matter balances gravity. Basically, feed it too fast and it chokes.
So, for a black hole to reach 66 billion solar masses, it would need a lot of time, way more than a few billion years. And yet, TON 618 was already this massive when the universe was still in its early teens.
It breaks the timeline. To make it even remotely possible, astronomers have proposed exotic theories. One, direct collapse black holes. Instead of forming from stars, maybe some black holes formed directly from giant clouds of primordial gas in the early universe. Skip the stars.
Go straight to the singularity. But even this can't fully account for the size. 2. Super Eddington accretion. What if TON 618 had a period of hyperfeeding, blowing past the normal limits?
Maybe it gobbled gas so fast that the radiation pressure never caught up. But we've never observed that happening. 3. Early formation plus mergers. Maybe it formed from a seed black hole that was already massive, then merged with other black holes again and again inside a dense starburst galaxy.
It's possible, but the math gets messy fast, and even the most aggressive models struggle to build something this big this early. So what we're left with is an object that seems to defy everything we think we know.
TONS 18 doesn't just test our understanding of black hole growth, it shakes the foundation of cosmology, and it raises terrifying questions. How many of these ultra-massive black holes are out there? Did we miss a key phase in the early universe?
Could there be black holes with trillions of solar masses, too faint or distant for us to detect yet? Here's something even more unsettling. We only found TON 618 because it's bright, it's active, it's feeding.
But when it stops feeding, when it becomes a dormant black hole, it'll go silent, invisible. We'd never know it was there. That means for every TON 618 we can see, there could be dozens more lurking, invisible, off the radar, holding galaxies in their gravitational grip.
TON 618 isn't just an object, it's a question mark, a mystery from a time we barely understand, a cosmic monument
to a process we may have fundamentally underestimated. It shouldn't have had time to get this big.
It shouldn't have been able to grow so fast. And yet, there it is, 10 billion light years away, still visible across the universe, still breaking the models we try to fit it into. So what do we do with an object like this?
We keep watching. We build better telescopes. We question the assumptions. And we remember, sometimes the universe doesn't whisper the rules. It screams the exceptions. There are things in the universe so extreme, they don't just break physics.
They bend it, literally. Because out there in the cosmos, there are objects so dense, so compact, that they actually warp time itself. Not metaphorically, not in sci-fi terms. Real, measurable time dilation, predicted by Einstein and proven by observation.
And nothing does this better or stranger than a neutron star. We've already talked about how neutron stars are compact, how they cram the mass of our sun into a space the size of a city.
But let's focus on what that actually means for space and time. Because this isn't just about density. It's about gravity so strong, it slows down time.
If you were to stand somehow on the surface of a neutron star, let's ignore the radiation and death for a second. Time for you would pass significantly slower than for someone far away, like floating in interstellar space. We're not talking milliseconds.
We're talking about minutes stretching into hours, depending on how close you get. This is pure general relativity at work. The greater the gravitational field, the slower time flows. And neutron stars are the perfect real-world demonstration. Here's the basic idea.
Gravity isn't just a force, it's a curvature in space. Massive objects distort the fabric of reality around them. They bend the geometry of the universe. Light bends, paths bend, even clocks slow down. This isn't theory anymore. It's measurable.
We see this with satellites near Earth. Time ticks slightly faster for GPS satellites than it does on the surface of Earth, just due to the difference in gravity. Now, scale that up. Near a neutron star, time slows dramatically.
Light itself has to climb out of the gravity well, stretching and shifting to longer wavelengths. This is called gravitational redshift, and it's one of the key ways we detect how warped time is around these objects.
But we're not done yet, because there's something even denser than a neutron star. You already know where this is going. Black holes don't just warp time, they bring it to a stop.
The closer you get to a black hole, the slower time moves relative to an outside observer. Get close enough to the event horizon, the point of no return, and time for you slows to a crawl.
From the outside, someone watching you fall in would see your clock ticking slower and slower until it appears to freeze entirely at the edge. That's not a trick. That's relativity in action. Inside the event horizon, things get even weirder.
The math says time and space swap roles. Time becomes a direction you can't avoid moving in, like falling down a well with no bottom. The singularity at the center is not just a place, it's a point in time you are destined to hit.
There is no stopping, no turning back, no surviving. So black holes don't just affect time, they redefine it. But even without crossing that point of no return, their influence is staggering.
Orbit a black hole close enough, say the one at the center of our galaxy, and your time will pass measurably slower than it does on Earth. That's not science fiction. It's been observed.
Stars orbiting Sagittarius A, the supermassive black hole in the middle of the Milky Way, show gravitational redshift. Their light is stretched as it climbs out of the gravity well.
Their clocks tick slower by fractions we can now detect with precision instruments.
In fact, this is one of the most direct tests of general relativity ever performed. And black holes keep passing with flying colors. So what does this mean? It means that time is not absolute.
It means that gravity is not just a force, but a geometry that changes depending on where and how close you are. And neutron stars, black holes, these are natural time machines.
Not in the jump to the future sci-fi sense, but in the very real, very terrifying sense that time itself behaves differently near them. Want a real mind-bender?
If you parked a spaceship near the edge of a neutron star and hovered there for a year, then flew back to Earth, more time would have passed on Earth than for you. Maybe decades, depending on how close you were.
You'd come home to a planet that aged while you barely changed. That's not hypothetical. That's gravitational time dilation. And it's happening all the time, subtly, even here on Earth. Astronauts aboard the International Space Station experience both gravitational and velocity-based time dilation.
After 6 months, they're technically a few milliseconds younger than their Earthbound counterparts. But near a neutron star, that difference becomes extreme. It becomes life-altering.
It becomes real enough to consider in future deep space missions, because how you measure time is no longer simple when time itself is relative to gravity. So next time you think of space as empty, quiet, still, remember this.
There are places out there where time ticks differently, where gravity stretches it, slows it, twists it. There are objects so dense that reality bends around them, and time itself becomes negotiable.
When people think of space, they usually picture emptiness, stars scattered in a sea of black. But that's only because we live inside a galaxy, one of billions, and most of what we see is crowded, bright, and structured.
Zoom out far enough, though, and you'll see something truly unsettling. The universe isn't just full of stars and galaxies, it's also full of nothing. Massive, yawning expanses of blackness called cosmic voids.
Holes in the large-scale structure of the cosmos, so big they make galaxy clusters look like ants crawling around the edge of a canyon. And these voids aren't small. We're talking hundreds of millions of light-years across.
Vast spherical regions with almost no galaxies, no matter, and no structure at all. Just thin whispers of hydrogen, a few scattered atoms per cubic meter, maybe the occasional rogue galaxy floating in isolation, but mostly nothing. These aren't random gaps.
They form a pattern, a massive, sprawling cosmic web. When we map the positions of galaxies on the larger scales, we see a structure emerge. Galaxies form filaments and clusters, long threads of matter, and in between those threads are the voids.
Imagine a 3D spider web with strands of light surrounding vast black bubbles. Now, magnify that by billions of light years. That's our universe. And one of the largest known examples is the Boötes void, sometimes ominously called the Great Nothing.
Discovered in 1981, it's about 330 million light-years in diameter, and it contains far fewer galaxies than it should. Statistically, a region that size should have thousands. The Boötes void, it has maybe 60. It's not just a hole, it's a cosmic desert.
And it raises a big question. How do you get a region of space so empty? The leading theory is that cosmic voids are the result of gravity and expansion working together.
After the Big Bang, tiny quantum fluctuations became slightly denser or slightly less dense regions. Over billions of years,
Gravity pulled matter into the denser areas, forming galaxies and clusters, while the underdense regions, the voids, were emptied out even further.
Matter gets pulled out, nothing is left behind, and the result is a universe that's not uniform but structured, sculpted by gravity, inflated by dark energy, and shaped by both presence and absence. And that absence is massive.
Voids can take up 80% of the observable universe by volume. Let that sink in. Most of space is not galaxies, stars, or dark matter. It's nothing. Not just low density, virtually empty. And yet, voids aren't completely dead.
They have structure, edges, weak gravitational fields. In fact, galaxies near the edge of voids are often moving away from them, as if being pushed out by the expanding low-density space inside.
This isn't a repulsive force, just the effect of higher gravity outside the voids pulling galaxies out of the underdense zone. In some cases, galaxies that do exist inside the voids, called void galaxies, are strange in their own right.
Often more isolated and less evolved than their smaller counterparts in denser regions. They don't collide as often. They age quietly, like cosmic hermits. And here's where things get really weird. Some studies suggest that if you lived inside a void, your measurements of the universe's expansion could differ slightly. Why? Because the geometry of space itself is different in those underdense regions.
That means your local universe might seem to expand faster or slower than average just based on your cosmic address. It's like living in a valley versus on a mountaintop. The curvature and slope change your perception of the landscape.
Now, scale that up to galactic proportions. And then there's the theoretical wild card. What if some of these voids aren't just accidents of cosmic structure, but evidence of something else?
Some fringe theories, still speculative but interesting, suggest that certain anomalous voids could be the result of early cosmic collisions, maybe with other pocket universes in a multiverse scenario.
If another universe bumped into ours in the early stages of inflation, it could have left a scar, a region of lower density expanding like a bubble in the sun. That's probably not the case for most voids.
But the fact that we can even ask that question seriously in physics papers tells you how strange these structures really are. Cosmic voids aren't black holes. They're not singularities. They're not regions of negative energy. They're just holes in the structure of the cosmos.
So vast, so smooth, and so empty, they seem unreal. But we can map them. We can measure their gravitational effects. We can see how galaxies bend around them, like stars navigating around the edge of an invisible crater. And the takeaway is haunting.
The universe isn't full. It's mostly missing. And the larger structures we don't know, they're places where things aren't. Places so huge, so empty, so quiet, they challenge the idea of what structure even means. They shouldn't exist in such numbers.
They shouldn't be so vast. They shouldn't take up most of everything. But they do. And they're not just a quirk. They're the skeleton of the cosmos. Gigantic holes, almost nothing inside, yet absolutely fundamental to how the universe is shaped.
One of the most unsettling discoveries in recent astronomy didn't come from some distant black hole or bizarre new particle. It came from looking back in time and seeing galaxies that shouldn't exist yet.
Galaxies that are too big, too mature, and too well formed to fit into any current model of how the universe evolved. And we found them right where they're not supposed to be at the beginning of time.
This story starts with the James Webb Space Telescope, JWST, the most powerful space observatory ever built. Its mission is to peer into the early universe, back when the first stars and galaxies were forming. And it worked too well.
Shortly after JWST began operations in 2022, astronomers pointed it toward some of the most distant light in the cosmos. The goal was to see the faint signatures of young forming galaxies, cosmic infants in their chaotic first few 100 million years of life.
But instead of baby galaxies, they saw something else. Massive structured, fully formed galaxies at redshifts higher than 10, meaning they existed just 300, 500 million years after the Big Bang.
At a time when, according to theory, the universe was still assembling its first basic building blocks. And yet, there they were, huge galaxies, some with stellar masses close to that of the Milky Way, containing billions of stars arranged in smooth elliptical shapes. Not chaotic lumps of gas, but well-organized structures that looked more like adult galaxies than newborns. That shouldn't be possible. According to our best simulations, like the Lambda CDM model, galaxy formation is a slow, messy process. Gas collapses, stars ignite, black holes form.
Over billions of years, gravity pulls things together into coherent shapes. But what JWST saw, that's like walking into a hospital maternity ward and finding a middle-aged man in a suit sipping coffee. Something doesn't add up.
And it's not just one galaxy or two, it's dozens. Early candidates like Glass Z13 and Sears 1749 appeared at redshifts of 11 to 14, meaning they formed within the first 400 million years.
More recently, studies have confirmed even heavier galaxies, some estimated to be 100 times more massive than what our models predicted could exist at that time. And they're not just large, they're chemically evolved.
Many of these galaxies show signs of heavy elements, oxygen, carbon, iron, which implies that generations of stars have already lived and died. In other words, they're not just old-looking, they're mature. How did this happen? We don't know.
But we have a few ideas. One, star formation may be more efficient than we thought. Maybe the early universe was a star-forming machine. Maybe gas collapsed faster. Maybe cooling was more efficient.
That would let galaxies form more stars more quickly, building mass in just a few 100 million years. The problem, that still doesn't explain the sheer scale of some of these early giants. 2, dark matter might behave differently.
If dark matter is more interactive or more clumpy in the early universe than we expect, it might have seeded structure faster. Galaxies could form earlier, drawn together by these unseen scaffolds. But again, no current model fixed the observed masses.
3. The cosmological timeline might be off. This one's radical. It suggests that the expansion rate of the universe, or the underlying physics of redshift, might be different than we think. That would affect our entire view of time and distance in cosmology.
But so far, no evidence supports this yet. 4. We're seeing a new class of galaxy. It's possible these aren't normal galaxies. Maybe they're ultra-compact starbursts. Maybe they're powered by massive black holes forming at the same time as their hosts.
Maybe they burn fast and die young, a kind of cosmic flashbulb we're only now catching in the act. Still, nothing fully explains how such mature structures appeared so early in cosmic history.
It's one of the biggest challenges the JWST has been thrown at cosmologists so far, and it's just getting started. If this trend continues, if more early massive galaxies keep showing up where there shouldn't be any, we may have to rethink galaxy formation entirely.
Not tweak it, rethink it. That means adjusting our simulations, revisiting our assumptions about star formation, and maybe even reworking parts of Big Bang cosmology. It's that big. For now, astronomers are careful. Some of these redshifts are still being confirmed.
Mass estimates are being revised. JWST is still in its early science phase, but the pattern is clear. Something is wrong with the timeline. We're seeing galaxies that look too evolved, too rich in stars, too chemically developed, way too early. They shouldn't exist.
But JWST is showing us that they do. And they are not just breaking the rules, they're rewriting them. In 2012, astronomers discovered a planet so strange it didn't match anything predicted by standard planetary formation models. It was large, light, and extremely low in density.
As if someone had taken a gas giant and inflated it with almost nothing. The planet is called Kepler-51b, and it is one of the least dense planets ever discovered. It's often compared to cotton candy because of how light and fluffy it is.
That's not a metaphor. It's a straightforward description of its measured density, less than 0.1 grams per centimeter cubed. For comparison, water is 1 GCC3. Saturn, the least dense planet in our solar system, is about 0.7 GDCE3.
Kepler-51b is about 0.3 grams per centimeter cubed, 20 times less dense than water. In other words, this planet is so low density that if you could find a bathtub big enough, it would float.
If you could scoop out a chunk of it, it would be lighter than styrofoam. Kepler-51b is located about 2,600 light-years away in the constellation Cygnus.
It orbits a sun-like star, and it was first detected by the Kepler Space Telescope via the transit method, which measures how a planet dims a star's light as it crosses in front of it.
Kepler-51b is part of a system with at least 3 planets, all orbiting very close to their star. What made this unusual system wasn't just the size of the planets. They're roughly the size of Jupiter, but how little mass they contain.
Despite being almost as wide as Jupiter, they're hundreds of times lighter. This kind of planet is now referred to as an ultra-low-density planet, or more casually, a superpuff. So, what makes Kepler-51b so puffy?
Current models suggest its atmosphere is composed mostly of hydrogen and helium, with very little heavy material. That alone would make it large and light. But the key factor seems to be its youth.
The Kepler-51 system is only about 500 million years old, extremely young compared to most known exoplanet systems. At that age, planets are still cooling off from formation. Their atmospheres are still inflated by internal heat.
Over time, many of these superpuff planets shrink as gravity compresses them and they lose some of their atmosphere. So we may be seeing Kepler-51b at a temporary stage before it condenses into something more stable.
But even with that explanation, this is an extreme example. This planet has a radius about 7 times that of Earth, but its mass is only about 2 Earths. That's far less than expected for a planet of its size.
When astronomers modeled its interior, they found that it would need an atmosphere hundreds of kilometers thick with a very low molecular weight to explain the observed data.
No heavy core, no dense materials, just a thick cloud of light gases surrounding a small warm center. It's also not stable long term. The planet orbits close to its star, which means it's bombarded by intense radiation.
Over time, this radiation will likely strip away its atmosphere, a process known as photoevaporation. As that happens, the planet may shrink dramatically, eventually becoming an Earth-sized rocky core or disappearing entirely. This makes Kepler-51b valuable as a case study.
It shows us a snapshot of early-stage planetary evolution, something we can't see in our own solar system, where all the planets are billions of years old and mostly stable. It also challenges how we define planets. Traditionally, we categorize planets by size: rocky planets, gas giants, ice giants. But Kepler 51b doesn't fit neatly into any of these groups. It's a gas giant in size, but not in mass. It's a gas dwarf in mass, but not in size.
If anything, it's a reminder that our classification system is still evolving, and that planets can exist with combinations of traits that seem contradictory. Kepler 51b is not alone either.
Other cotton candy planets have been found, including Kepler 51c and Kepler 51 in the same system, but Kepler 51b remains one of the best studied and most extreme examples.
A planet that big with so little mass should not be able to hold itself together for long. Yet it does for now. And as telescopes like JWST continue to study its atmosphere, we'll learn more about how planets form, how they lose their gases, and how long superpuffs like this can survive before collapsing or evaporating completely.
It shouldn't exist in this state, but we caught it in the act. And it's a reminder that planets can be as light as foam and still orbit like giants. In physics, there's a strict rule.
Nothing can travel faster than the speed of light in a vacuum. It's a fundamental limit built into the structure of special relativity. But in cosmology, there's an exception. And it's not a loophole. It's a feature of how space itself behaves.
Many galaxies in the universe are moving away from us at speeds that exceed the speed of light, not because they are traveling through space faster than light, but because space itself is expanding between us and them. This is called metric expansion. And it's one of the central ideas in modern cosmology. It means that on large scales, the fabric of space stretches over time, increasing the distances between objects that are not gravitationally bound. Here's how it works.
After the Big Bang, the universe has been expanding. The farther away a galaxy is, the faster it appears to recede from us. This is described by Hubble's law, which states V equals h0 equals d, where v is the galaxy's recession velocity, h0 is the Hubble constant, rate of expansion, and d is the distance to the galaxy.
There is no upper limit on d, so if a galaxy is far enough away, its calculated recession velocity v can exceed the speed of light. For example, galaxies more than about 14.4 billion light-years away are receding from us faster than 299,792 kilometers per second, the speed of light. And that distance gets smaller as the expansion of the universe accelerates due to dark energy.
This does not violate relativity. Here's why. Special relativity says nothing can move through space faster than light. But general relativity allows space itself to expand, and that expansion is not limited by the speed of light.
The galaxies themselves are not moving through space that fast. They are being carried away by the expansion of the universe. You can think of it like dots on a balloon. As the balloon inflates, the dots move away from each other.
They are not moving on their own. The surface beneath them is stretching. In this analogy, light-speed limits don't apply to the balloon's expansion rate. So, what happens to galaxies moving away from us faster than light? They become unreachable.
Light emitted from these galaxies today will never reach us. Even though they may be visible now because their light was emitted billions of years ago when they were closer, there will come a point where their distance becomes so great that any future light they emit will be redshifted away permanently.
This boundary is called the cosmic event horizon.
It marks the limit beyond which objects are moving away so quickly that light from them can never reach Earth, no matter how much time passes.
It's important to separate this from the observable universe, which is the region from which light has had time to reach us since the Big Bang, about 46.5 billion light-years in radius.
But even within that range, some galaxies are already receding faster than light, and their light is effectively lost to us after a certain point. This also means that the observable universe is shrinking in a practical sense, not in size, but in accessibility.
Over billions of years, more and more galaxies will cross the cosmic event horizon and become undetectable. Eventually, only the local group, our own gravitationally bound group of galaxies, including the Milky Way and Andromeda, will remain visible.
All other galaxies will redshift out of sight. This has serious implications for the future of cosmology. In a few trillion years, astronomers in our galaxy will see a black sky with no external galaxies visible.
There will be no observational evidence of an expanding universe. From their perspective, it might look like the universe is static and empty. In other words, our current ability to study the cosmos is time-limited.
We live in a brief window of time when the light from distant galaxies still reaches us, just before they become permanently invisible. So how do we observe galaxies moving faster than light? We detect them using their redshift.
The stretching of light waves due to expansion. The higher the redshift, the faster the galaxy is receding. Galaxies where the redshift's greater than about Z1.4 are already moving away faster than light.
Some of the most distant known galaxies and quasars have redshifts of Z equivalent to 10 or higher, meaning their recession velocities are far beyond the speed of light.
We can see them now because the light was emitted long ago when they were closer, but they are now well beyond our cosmic reach. To summarize, galaxies are not breaking the light speed limit by moving through space.
Space itself is expanding, and this expansion is not constrained by the speed of light. Distant galaxies are moving away faster than light due to this expansion. Light from galaxies beyond the event horizon will never reach us.
This process gradually isolates our galaxy from the rest of the universe. These galaxies should not be visible based on ordinary velocity rules. But because the universe isn't static, the rules of expansion allow it. They move faster than light.
And yet we see their ancient light for now. In 2020, astronomers announced the discovery of a star orbiting a black hole at a velocity that should not be possible for normal stellar systems.
The star is named S47 H Sphinx, and it orbits Sagittarius Ecurich, the supermassive black hole at the center of our galaxy. During its closest approach, or pericenter, the star travels at approximately 24,000 kilometers per second. That is 8% of the speed of light.
To put that in perspective, Earth orbits the Sun at about 30 kilometers per second. Mercury, the fastest planet in our solar system, moves at 47 kilometers, S471, Saints. S471 moves 500 times faster than Mercury.
S47 Wild completes one full orbit around Sagittarius ASD in just 4.0 years, making it the fastest known star in close orbit around the black hole.
Its elliptical orbit brings it as close as 100 astronomical units AU from the black hole at its pericenter. That's about 15 billion kilometers, or 2.5 times the distance between the Sun and Neptune.
This is extremely close, considering the gravitational field it's moving through. Sagittarius A has a mass of about 4 million times the mass of the Sun. The gravity near it is strong enough to significantly affect space and time.
Meaning, S4716 is not only moving quickly, but also experiencing measurable gravitational time dilation and orbital precession, both of which are predicted by general relativity. The star was identified using high-resolution infrared observations from instruments like Gravity on the Very Large Telescope Interferometer in Chile and Keck Observatory in Hawaii.
These facilities have been monitoring the region around Sagittarius A for over 2 decades, tracking the motion of stars that form a cluster known as the S cluster or star group. S47116 is the fastest and closest stable orbiting member of this group observed so far.
These stars are useful not only because of their extreme speeds, but also because they allow astronomers to study the black hole's gravitational environment in detail.
The motion of S407 on sand and nearby stars can be used to measure the mass of Sagittarius A with high precision, confirm predictions from Einstein's general relativity, detect any deviations that might indicate unknown physics. One such prediction is Schwarzschild precession.
The way an orbit shifts over time due to the curvature of spacetime. In Newtonian gravity, orbits are closed ellipses. In general relativity, they precess, meaning each orbit traces a slightly different path. This effect has been observed in SCS 7160's orbit.
The discovery of such a fast orbit raises questions about how a star like this can survive so close to a supermassive black hole. Any closer, and the star would likely be destroyed by tidal forces.
Difference in gravity between the black hole's near and far side would stretch the star until it breaks apart. Yet S4716 stays intact. The current explanation is that S4016 may have been part of a larger system, like a binary star, that was disrupted by the black hole's gravity.
In such an event, one star is ejected at high speed, possibly becoming a hypervelocity star, while the other is captured into a close orbit, like S4711-16. This scenario could explain how stars end up in tight, fast orbits around Sagittarius A without being destroyed.
It also suggests that stellar interactions near supermassive black holes are common, and that the center of the galaxy is a highly dynamic environment. S4716 is not unique in principle, but it is the most extreme case observed so far.
Its existence confirms that stable short-period orbits can exist within a 100 AU of a supermassive black hole. Relativistic speeds are possible for stars under extreme gravitational influence. Tidal limits are broader than previously estimated for complex stars.
These measurements also help calibrate models of galactic centers in other galaxies where direct resolution of individual stars is not yet possible. In summary, S41716 orbits Sagittarius A every 4 years. It reaches speeds of 24,000 kilometers or west, 8% of the speed of light.
It follows a stable elliptical orbit only 100 AU from the black hole. Its motion confirms predictions of general relativity. It helps refine our understanding of dynamics near black holes.
A star moving at relativistic speed, orbiting a supermassive black hole at the core of our galaxy, should be rare and difficult to detect. But S4716 proves such stars exist and can survive in one of the most extreme environments known.
In 2008, a team of astrophysicists announced the detection of a large-scale motion in the universe that could not be explained by known forces or structures. This motion was called dark flow.
It refers to a group of galaxy clusters, some of the most massive structures in the universe,
moving together at unusually high speeds in a single, consistent direction across hundreds of millions of light years.
The velocity involved is significant, between 600 and 1,000 kilometers per second, directed toward a region of sky near the constellations Centaurus and Hydra. This movement is not expected under standard cosmological models.
According to the LCDM model, lambda, cold dark matter, the universe's large-scale structure should exhibit random motion except for the expansion driven by dark energy.
Any peculiar velocities, motions not due to cosmic expansion, should cancel out on large scales, especially beyond 300 million light years. But the dark flow doesn't cancel. It continues. How was this measured?
The effect was first detected using data from the Wilkinson Microwave Anisotropy Probe, WMAP. The team analyzed the cosmic microwave background, or CMB, specifically how its light was scattered by hot gas in distant galaxy clusters.
They looked at the phenomenon called the kinematic sandwich effect, KSZ. This happens when photons from the CMB pass through moving galaxy clusters and are slightly shifted due to the motion of electrons in the cluster's hot gas.
By measuring small temperature shifts in the CMB caused by this interaction, researchers could estimate how fast and in what direction the galaxy clusters were moving. What they found was unexpected.
A coherent flow of hundreds of galaxy clusters, all heading in the same direction beyond the range where such motion should exist. The pattern extended to a distance of over 2.5 billion light-years.
And crucially, this motion was not aligned with the structure of the observable universe. It didn't match the distribution of galaxies or known gravitational sources. What could cause this? The standard model does not predict this kind of large-scale bulk flow.
Several possible explanations have been proposed. Measurement error. Some scientists argue that the signal is too close to the detection threshold and may result from systematic error, instrument noise, or data processing artifacts. Gravity pulled from outside the observable universe.
One of the more controversial theories suggests that the motion is caused by massive structures beyond our cosmic horizon, areas we cannot observe because light has not had time to reach us.
These superclusters or other forms of matter could be exerting a gravitational influence on local structures, creating a pull effect across billions of light years. Anisotropy in the early universe. Another idea is that the early universe was not perfectly uniform. If inflation, the rapid expansion after the Big Bang, had irregularities, they could cause asymmetric motion that persists today. Multiverse theories. Some speculative models propose that our universe may be interacting with other universes.
If a neighboring bubble universe exists and has gravitational influence, it could theoretically produce large-scale directional flow in our own. Has it been confirmed? The existence of dark flow remains unconfirmed.
Follow-up studies using different data sets, including those from the Planck satellite, have produced mixed results. Some found no significant evidence for the flaw. Others replicated part of the signal, but with lower confidence. The debate is ongoing.
The original WMAP study, led by Alexander Kashlinsky, has continued to support the finding, but other research groups have raised doubts, especially concerning the challenges of measuring the weak KSEZ signal over cosmic distances.
Despite this uncertainty, the concept of dark flow is taken seriously because of what it would imply, that the observable universe is not self-contained, and their structures or conditions outside our visible region may be affecting what we see.
If dark flow is real, It would require an update to the standard cosmological model, or even an entirely new framework to describe the universe's large-scale dynamics. Key facts. Dark flow refers to coherent motion of galaxy clusters toward a single direction.
Detected velocities range from 600 to 1,000 kilometers second, observed over scales larger than 1 billion light-years. Measured using the kinematic Zeldovich effect. Cause remains unknown. Possibilities include unseen mass beyond the observable universe.
Early universe anisotropy anisotropy, or measurement error, remains an open question in cosmology. The concept challenges the idea that the universe is isotropic and homogeneous on large scales, a fundamental assumption in cosmology.
Whether it's real or not, the search for the truth behind the dark flow is forcing astronomers to look deeper and further than ever before.
In 2006, astronomers released an observation that became one of the strongest pieces of evidence for the existence of dark matter. It came from a collision between two galaxy clusters, known collectively as the Bullet Cluster.
This system is located about 3.88 billion light-years away in the constellation Carina, and is composed of two galaxy clusters that pass through each other at high speed, leaving behind a clear separation between different types of matter.
When galaxy clusters collide, three main components interact: stars, hot gas, and dark matter. The stars, which are separated by large distances, mostly pass through each other unaffected.
The hot gas, which makes up most of the normal matter in the cluster, is slowed down by drag interaction. Dark matter, if it exists, should behave like the stars and continue moving forward without interacting much.
To study this event, astronomers used data from the Chandra X-ray Observatory and optical images from ground-based telescopes. The hot gas was mapped in X-rays, while the distribution of total mass, including dark matter, was inferred using gravitational lensing.
Gravitational lensing is a phenomenon where the mass of a foreground object bends the light from background galaxies. By analyzing distortions in the shapes of those background galaxies, researchers created a map of where the mass in the cluster is located.
What they found was a clear separation. The hot gas, visible in X-rays, lagged behind, but the gravitational lensing map showed that most of the mass had already moved ahead in the same direction as the galaxies.
This indicated that the majority of the cluster's mass was not in the gas, but in some invisible component that passed through unaffected. That invisible component matched what dark matter is expected to do.
This result is significant because it directly contrasts with modified gravity theories. Alternative explanations to dark matter, like MOND, M-O-N-D, modified Newtonian dynamics, suggest that the effects we attribute to dark matter might be due to a different law of gravity on cosmic scales.
But the Bullet Cluster shows that mass and visible matter have physically separated. This observation cannot be explained by modifying gravity alone. It requires an unseen component of mass that interacts gravitationally but not electromagnetically. In other words, dark matter.
The Bullet Cluster is also a high-speed collision. The subcluster, which gives the system its name, is moving at a velocity of roughly 4,500 kilometers per second.
The shock wave generated by this motion heats the gas to over 100 million Kelvin, producing a visible bow shock in X-ray images. This further emphasizes how violently the normal matter was disrupted, while the dark matter kept moving undisturbed.
Since the initial discovery, other similar collisions have been studied, but none show the separation as clearly as the bullet cluster. It remains the cleanest example of dark matter and normal matter decoupling during a large-scale cosmic event.
The bullet cluster does not prove what dark matter is made of, but it confirms that there is mass that does not emit or absorb light, that interacts primarily through gravity, and that is not part of the hot gas for stars.
This supports the current model, where dark matter makes up roughly 85% of the matter in the universe. While direct detection of dark matter particles is still ongoing in laboratories on Earth, the bullet cluster provides a direct observable astrophysical case where dark matter's effects are visible and measurable.
Its importance in cosmology is fundamental because it visually and quantitatively demonstrates that most of the matter in a galaxy cluster is not the matter we can see. In 2011, astronomers identified an object called CFB-SDR 040238.
It appeared to be a planet-sized body moving through interstellar space, with no star to orbit. This object did not reflect light from a nearby sun, showed no signs of a host system, and did not fit into the traditional model of a planet orbiting a star.
It was traveling independently. This made it one of the first strong candidates for what is now known as a rogue planet. Rogue planets, also called free-floating planets or orphan planets, are planetary mass objects that drift through the galaxy without being gravitationally bound to any star.
They exist on their own, untethered, and may be found anywhere in interstellar space. These planets are not rare anomalies. The more data astronomers gather, the more evidence suggests they are likely common, perhaps even more numerous than stars.
There are several proposed origins for rogue planets. Some may have formed in isolation from collapsing gas clouds, similar to how stars and brown dwarfs form, but on a smaller scale. These are called primary rogue planets.
Others may have formed normally within a solar system, but were later ejected due to gravitational disturbances. These are called secondary rogue planets. The ejection of a planet from its host system can happen in multiple ways.
A common scenario involves a close encounter between two massive planets where one planet is flung outward by the other during early system formation. Another possibility is an external disruption, such as a passing star, whose gravitational field destabilizes planetary orbits, ejecting a planet into interstellar space.
Once ejected, the planet travels indefinitely, no longer influenced by its former star. Detecting rogue planets is difficult, primarily because they are dark. Unlike stars or planets with host stars, rogue planets do not reflect light from a central source.
Most of the techniques astronomers use to detect exoplanets, like the transit method or radial velocity method, are ineffective without a nearby star. Instead, astronomers rely on techniques like gravitational microlensing and infrared observations.
Gravitational microlensing occurs when a massive object passes in front of a more distant star, briefly magnifying the background star's light due to the gravitational bending of light. This method does not depend on the planet emitting or reflecting light.
Instead, it reveals the presence of mass. Using this technique, projects like OGLE, Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in Astrophysics, have detected several rogue planet candidates.
One such detection was made in 2020, when a microlensing survey revealed an Earth mass object moving across a star field with no visible host. It was the first known rogue planet with a mass close to Earth's, suggesting that not all rogue planets are gas giants.
There may be billions of rocky, Earth-like rogue planets drifting in the galaxy, completely hidden from view except for rare lensing events. Infrared telescopes can also detect larger rogue planets, especially those that are young and still radiating heat from their formation.
Young planets retain internal energy that cause them to emit in the infrared spectrum. Instruments like the WISE Wide Field Infrared Survey Explorer have identified several cold substellar objects that are likely planetary mass and not associated with any star.
CFBD-SIR suggests 0403 remains a prominent example. Initially estimated to be between 4 and 7 times the mass of Jupiter, it appears to be between 100 and 500 million years old. It has a surface temperature of roughly 400 to 700 Kelvin.
These values are based on modeling its thermal emission in the absence of starlight, which is a difficult and imprecise process. Later studies questioned whether it was a planet or a low-mass brown dwarf, which demonstrates how difficult classification can be when no host star is available to provide orbital context.
Whether gas giant or brown dwarf, CFP fits the operational description of a rogue planet, a planetary mass object without a star. Rogue planets have several implications for planetary science and astrobiology.
Even without a star, a large rogue planet could potentially sustain internal geological activity. If it has a molten core and enough radioactive decay inside, it could retain heat for billions of years.
If that heat is trapped beneath the thick atmosphere, particularly one rich in hydrogen, it might create conditions where subsurface liquid water could exist. Some models even suggest that an Earth-sized rogue planet with a dense hydrogen atmosphere could maintain surface temperatures above the freezing point of water. This leads to the question of whether such planets could support life. Life on Earth depends on sunlight, but deep-sea ecosystems survive without it, relying instead on geothermal energy.
A similar process could, in theory, occur on a rogue planet, particularly one with subsurface oceans protected from the cold of interstellar space. There are no confirmed life-hosting rogue planets, but they demonstrate that a planet does not need to orbit a star to be thermally active or potentially habitable in some limited form.
Rogue planets also challenge definitions. The International Astronomical Union defines a planet partly by its orbit, specifically that it orbits a star. Rogue planets do not, yet they clearly share mass and structural characteristics with bound planets.
Some astronomers propose alternative classifications, such as sub-brown dwarfs or isolated planetary mass objects, but the term rogue planet remains widely used. The existence of rogue planets also affects models of star system formation.
Simulations suggest that planetary systems often experience instability in their early stages. If ejection events are common, it would explain why so many rogue planets are detected.
It also raises the possibility that many stars formed with more planets than they currently host, with the missing planets now drifting far from their original systems.
The current estimate is that there could be 2 or more rogue planets for every star in the Milky Way. That means there may be hundreds of billions, possibly trillions of such objects in our galaxy alone.
They do not emit visible light, and most will never come close enough to be detected. They are part of the galaxy's mass, but invisible under most conditions. Occasionally, a rogue planet might pass through a planetary system or near a star.
In some cases, it could be captured into orbit, becoming part of a new system. In others, it might pass undetected.
The likelihood of such events is low due to the vast distances between stars, but over cosmic time, rare interactions can occur.
Rogue planets are a natural consequence of gravitational dynamics. They are not rare failures of planet formation. Instead, they are products of how systems evolve, stabilize, and sometimes eject their own planets. Their isolation does not make them anomalies.
It makes them typical of the dynamic nature of space. They are planets, but without a system. They drift in the cold, not because they failed to form normally, but because the universe made them mobile. As astronomers have cataloged thousands of exoplanets, one category has consistently rejected expectations: planets with highly elliptical orbits. These orbits are far from circular. Instead of moving smoothly around their stars in predictable paths like the planets in our solar system, these exoplanets swing in and out in extreme arcs, at speeds and distances that raise questions about how they remain in orbit at all.
In physics, orbital stability is a balance between gravitational pull and orbital velocity. In our solar system, the planets follow mostly low eccentricity orbits. Earth's orbit, for example, is almost a perfect circle, with an eccentricity of about 0.017.
Even Pluto, once considered an outlier, has an eccentricity of just 0.25. But many exoplanets have orbits that are much more extreme. Some have eccentricities of 0.6, 0.7, or even higher, meaning they spend part of their year skimming close to their host star and the rest of it flung far into deep space.
These kinds of orbits should produce large temperature swings, complex gravitational interactions, and potential long-term instability. Yet some of these planets appear to have persisted in these orbits for billions of years. One example is the exoplanet HD 2000 Spencer-Aister II. Located about 117 light-years away, it holds the record for the most eccentric planetary orbit discovered to date, with an eccentricity of 0.96. This means its orbit is almost a straight line.
At its closest point, it comes within 0.06 astronomical units, AU, of its star, closer than Mercury is to the Sun. At its farthest, it stretches out beyond 2.5 AUs, farther than Mars.
This creates a drastic swing in distance and presumably in temperature and radiation exposure. HD 2782b is a gas giant with a mass about 1.9 times that of Jupiter. Its orbital period is about 586 days.
During its close approach, it receives more than 100 times the radiation it does at its farthest distance. This should result in atmospheric instability or extreme heating, but the planet appears to remain intact and in orbit.
How a planet maintains such an orbit without being destroyed or ejected is not fully understood.
Another example is Fomalhaut b, once thought to be a planet with a similarly strange trajectory, though later data suggested it might not be a planet at all. The system still illustrated the kind of path that some planetary mass bodies might follow, showing highly extended orbits that take them far outside the plane of the host system.
These eccentric orbits are difficult to explain through traditional models of planet formation. Most planets are thought to form in a protoplanetary disk, a rotating flattened disk of gas and dust around a young star. The natural motion of this disk leads to circular orbits.
So, how do we get elliptical paths? Several mechanisms have been proposed. One is planet-planet scattering. In a young planetary system, multiple large planets may interact gravitationally,
if one planet moves slightly off its original orbit. Repeated interactions can build over time, eventually kicking one planet into an eccentric orbit or rejecting it entirely. The survivors may end up in long elliptical paths, which then stabilize over time.
Another possibility is interaction with a binary star. If the host star has a distant stellar companion, its gravitational pull can perturb planetary orbits. This effect, known as the Kusai leadoff mechanism, can amplify orbital eccentricity over time.
It periodically trades inclination for eccentricity, causing the planet to move in an increasingly elongated orbit. These cycles can last for thousands or millions of years, during which the orbit becomes more extreme before possibly returning to a more circular path.
There's also the influence of fly stellorbes. In crowded star-forming regions, close encounters between young stars are common. If another star passes near a planetary system, it can destabilize the orbits, sending some planets inward, outward, or ejecting them altogether.
A planet knocked out of its original orbit might settle into an elongated path if it escapes complete removal. The key problem with highly elliptical orbits is the long-term stability.
These orbits subject planets to extreme tidal forces, especially during close passes to the host star. Depending on the star's mass and the planet's structure, this can cause significant heating or even physical deformation.
In some cases, the planet may lose atmosphere, shed material, or develop an unusual thermal profile. Yet despite these risks, some elliptical orbit planets appear to remain intact for hundreds of millions of years. Simulations have shown that such orbits are often metastable.
That means they may persist for long periods, but could still be vulnerable to eventual disruption, particularly if there are other large bodies in the system or if the star itself evolves. As the host star expands or loses mass later in life, orbital dynamics will shift. A planet with an eccentric orbit may eventually be drawn in or fun out. There are also questions about what happens to any potential moons or rings around these planets.
A moon orbiting a planet on a circular path has a relatively stable environment. But if the planet is on a long elliptical orbit, the gravitational stresses during a close approach could destabilize the moon's orbit, either pulling it into the planet or ejecting it into space.
Tidal heating within moons could also vary dramatically, potentially affecting their geology. Atmospheric modeling for these planets is also complex. A gas giant that spends part of its orbit near its star will experience intense heating and atmospheric expansion, followed by long periods of cooling.
This can lead to temporary temperature inversions, changing cloud chemistry, and dynamic weather systems. In extreme cases, the atmosphere could undergo partial escape or recondensation cycles, depending on how cold it becomes at aphelion.
Some elliptical orbit exoplanets are also part of multi-planet systems, which raises additional challenges. If one planet has an eccentric orbit, it can destabilize others unless their orbits are finely tuned. The system must maintain delicate gravitational relationships, especially over millions of years.
Despite all of these complexities, surveys like those from the Kepler Space Telescope, the HARP spectrograph, and other exoplanet missions continue to uncover more examples. This suggests that highly eccentric orbits may not be rare.
They might represent a common evolutionary phase in planetary systems, especially during or after periods of instability. These planets show that stable planetary orbits are not limited to near-circular paths.
Under the right conditions,
Planets can survive in shapes and trajectories far outside what is observed in our solar system. These orbits shouldn't last forever, but in the timescales we can observe, they hold.
In 2015, astronomers detected an exoplanet that was actively losing its atmosphere in real time, essentially disintegrating as it orbited its star. The planet, named KIC 12V4S2b, was found by NASA's Kepler Space Telescope, and its light curve immediately stood out as unusual. Instead of a clean, regular dip in brightness that indicates a solid planet crossing in front of a star, the signal varied irregularly in both depth and shape, sometimes with shallow transits, sometimes with deeper ones, and often with asymmetric patterns.
This was the first evidence that something was not just orbiting the star, but breaking apart as it did so. KIC 1257 orbits its host star roughly every 15.7 hours.
This means it is extremely close to its star, less than 2 stellar radii away. At this proximity, the planet receives enormous amounts of radiation and heat. Estimates suggest the surface temperature on the star-facing side of the planet could reach 2,000 degrees Celsius or more.
At these temperatures, solid rock doesn't just melt, it vaporizes. The prevailing interpretation is that the planet is a small rocky body that is being evaporated by stellar radiation, forming a tail of dust and gas, trailing behind it like a comet.
As the planet moves around the star, this tail causes changes in the amount of light blocked during each transit. Sometimes the dust cloud is larger or more opaque, causing a deeper dip in brightness. Other times, it's smaller, producing a shallower signal.
The variability and shape of the light curve match models of a planet losing mass into space. Estimates suggest the planet may be losing mass at a rate of 1 Earth mass every billion years.
That might sound slow, but for a small planet, perhaps only Mercury-sized, this rate could result in total destruction in under 1 billion years.
If the process has already been ongoing for some time, it's possible we are witnessing one of the final stages in the planet's existence. The planet's mass has not been precisely measured, but it's believed to be less than half the mass of Mercury.
It's small enough that it cannot hold on to its atmosphere under such intense radiation. The gravitational pull of the star strips material away, and solar wind pushes it outward, forming a tail that can stretch for tens of thousands of kilometers.
The tail is likely composed of silicate particles, essentially vaporized rock that has recondensed dust. This dust reflects and absorbs light, which is what Kepler detected during transits. This phenomenon is not unique to KIC 127548b.
Other candidates for evaporating or disintegrating planets have been found, including KOI 2700b and WD 1145 plus 17b. The latter is particularly notable because it orbits a white dwarf, the collapsed remnant of a once normal star.
In that case, debris from a destroyed planet is seen falling into the white dwarf, showing that evaporation and disintegration can continue even after a star has completed its life cycle. The idea of planets being destroyed by their stars is supported by physics.
At very close orbital distances, planets receive intense stellar flux, especially in the ultraviolet and X-ray parts of the spectrum. This energy can ionize atmospheric particles, heating them to the point where they reach escape velocity.
The result is hydrodynamic escape, a process where the planet's upper atmosphere expands outward and escapes into space. In gas giants, this leads to the loss of hydrogen and helium.
In rocky planets, it can strip away lighter elements, and at high enough temperatures, even metals and silicates can vaporize.
The fate of CIC 127 FUM 48b also gives clues about planetary migration. It's unlikely that the planet formed so close to its star.
Instead, it probably formed farther out and migrated inward over time due to gravitational interactions or orbital decay. Once it moved into a close orbit, the high-energy environment began stripping it apart.
This process is part of what shapes planetary systems over billions of years. Planets move, interact, and sometimes get destroyed. There are theoretical models that describe how close a planet can orbit before it is physically disrupted. This distance is known as the Roche limit.
For fluid or partially molten bodies, getting too close to a star means that tidal forces can begin pulling the planet apart. Key 11/12 FM, wafer 48b, is not quite within the Roche limit, but it is close enough that radiation pressure and thermal evaporation are having a visible effect.
If the planet continues to lose mass, it may eventually cross the Roche limit and be torn apart completely. The detection of disintegrating planets raises several scientific questions. One is about the composition of the dust.
Models suggest silicates like pyroxene and olivine are likely candidates, similar to minerals found on Earth. Spectroscopic studies eventually detect the specific composition of the cloud. Another question is how long the process can continue before the planet is gone.
Current estimates that some of these planets have already lost a large fraction of their original mass. We may be observing the final 1,000,000 or 100,000 years of their existence, a brief period in astronomical terms.
These systems are also useful for testing planet-star interaction. As a planet disintegrates, it deposits material into the stellar environment. Over time, this could affect the star's spectrum, possibly leaving detectable signatures in the stellar atmosphere.
It also contributes to the broader understanding of how planetary systems evolve, especially in extreme environments. The discovery of these planets was only possible because of precise and continuous monitoring.
Kepler's ability to detect small changes in brightness over many years allowed astronomers to identify subtle variations that other instruments might have missed. The unusual transit profiles, asymmetric dips, variable depths, were the key indicators that something unusual was happening.
More such planets may be discovered by future missions like TESS, Transiting Exoplanet Survey Satellite, and Plato. These missions are designed to monitor large sections of the sky and identify short-period planets with unique light curves.
As data improves, more disintegrating planets may be cataloged, giving researchers a statistical view of how common this process is. K-Zoisicone 8b and similar objects show that planetary destruction is not a rare or theoretical event.
It is something we can observe, measure, and study in detail. These planets exist in environments that test the limits of material stability. Their proximity to the stars places them in a constant state of decay.
They are not being destroyed instantly, but gradually, over thousands or millions of orbits. We often think of planets as stable and long-lived, but these systems show that planets can have lifespans shorter than Earth's.
In these cases, planets are not just orbiting their stars. They are being consumed by them, bit by bit, layer by layer, until nothing remains but a trail of dust and vapor.
And in the time we've been watching, we may be witnessing the final chapters. In 2005, NASA's Cassini spacecraft made a discovery at Saturn that changed our understanding of where active processes and possibly even conditions for life could exist in the solar system.
As it flew by Saturn's small moon, Enceladus, Cassini captured images of plumes of material being ejected from the moon's south pole. These were not clouds or surface winds.
They were geysers, jets of water vapor and ice particles being blasted into space from beneath the moon's icy crust. This phenomenon was unexpected. Enceladus is only about 500 kilometers in diameter, roughly the width of the state of Arizona.
It's small, cold, and coated in reflective ice. Until then, most scientists assumed it was a frozen, inactive body. But Cassini revealed that Enceladus is geologically active with cryovolcanic geysers that launch material hundreds of kilometers above the surface and into space. The plumes originate from long fractures in the ice, nicknamed tiger stripes. These stripes, more formally called sulci, are regions of warmer terrain that show evidence of stretching and cracking.
Cassini's instruments confirmed that the material being ejected was mostly water vapor, along with ice particles, salts, ammonia, molecular hydrogen, and organic compounds. The presence of molecular hydrogen was particularly important in Earth's oceans.
Molecular hydrogen is produced through a process called serpentinization, where seawater interacts with hot rock. This reaction provides energy that can fuel microbial life in deep-sea hydrothermal vents.
On Enceladus, the same kind of chemistry may be occurring in an ocean beneath its icy shell, making the moon one of the most promising locations in the solar system to search for extraterrestrial life.
The geysers suggest that Enceladus has a subsurface ocean beneath an outer ice crust that may be only 20 to 30 kilometers thick in some areas. Beneath that is believed to be a liquid saltwater ocean in direct contact with a rocky core.
Heat from tidal forces caused by Saturn's gravitational pull and the Moon's slightly elliptical orbit may keep this ocean from freezing, allowing for liquid water and geological activity. Cassini didn't just observe the geysers from a distance.
It actually flew through the plumes on several occasions, using its mass spectrometer to sample their composition directly. The measurements confirmed that the material came from a liquid source, not surface sublimation.
In fact, the ejected particles form part of Saturn's E-ring, showing that Enceladus is actively replenishing it. One of the most remarkable findings was the chemical complexity of the plume material. Cassini detected simple organic molecules, salts, silicon nanoparticles, and complex carbon-bearing compounds.
These are the building blocks of life. While no life was found, the environment inside Enceladus, water, heat, energy sources, and organics meets many of the criteria for habitability.
Scientists estimated that the geysers eject about 200 kilograms of material per second, and that the jets can reach hundreds of kilometers in height, escaping the moon's gravity.
Some of the material falls back as icy snow, while some is lost to space or absorbed into Saturn's rings. Enceladus is not the only icy moon with possible subsurface oceans, but it is one of the few where material from the ocean escapes into space, making it accessible for direct sampling without needing to land or drill.
This makes future missions to Enceladus a high priority. NASA has considered proposals like the Enceladus Life Finder or the Orbolander, which would fly through or land near active plumes to study the chemistry in detail, looking for biosignatures, molecular evidence of life.
The sustained activity of these geysers also means that Enceladus is not just active now, but likely has been for millions of years. The heat generated by tidal flexing is enough to maintain a liquid ocean
over geological timescales.
Especially with the insulating effect of the ice shell, models suggest that the energy balance on Enceladus could be stable, allowing for long-term liquid environments beneath the surface. The discovery of Enceladus's geysers shifted scientific thinking about where habitable conditions might exist.
Previously, the search for life focused on planets or moons within a star's habitable zone, where surface temperatures allow for liquid water. Enceladus shows that internal heating can create ocean environments even in the outer solar system, far from the Sun.
This has implications for other moons like Europa, Ganymede, and even Titan, which may have similar oceans beneath their ice shells. The activity on Enceladus also raises questions about how such a small moon can remain geologically active.
Normally, small bodies cool quickly and freeze solid, but the combination of a liquid ocean, orbital resonance with other moons like Dione, and a rocky core that facilitates tidal heating seems to give Enceladus an internal heat engine that sustains the geysers.
In addition to providing data about potential habitability, the geysers help scientists study the moon's interior indirectly. By analyzing the chemistry, temperature, and particle composition of the plumes, researchers can infer the properties of the ocean, the thickness of the ice, and the nature of the sea floor.
This is especially useful because drilling through 20 kilometers of ice would be a major engineering challenge. In 2018, scientists reanalyzed Cassini data and found evidence of complex macromolecular organics, large carbon molecules that are much more chemically sophisticated than methane or ammonia.
While not a sign of life, these molecules suggest a rich chemistry that could, in theory, support biological processes if microbial life were present. Enceladus's geysers represent one of the most direct ways we have of accessing an extraterrestrial ocean. Unlike other ocean worlds that are sealed off, Enceladus brings samples from its subsurface environment directly into space. This makes it an ideal target for future missions looking to detect signs of life beyond Earth.
Despite its small size, Enceladus has proven to be one of the most geologically and scientifically interesting objects in the solar system. The geysers continue to erupt, possibly for millions of years to come, providing a continuous stream of data and potential for discovery.
The icy surface of the moon, the cracks that stretch for kilometers, and the massive columns of water vapor shooting skyward all demonstrate that even in the cold reaches of the outer solar system, dynamic activity can persist.
Enceladus doesn't just challenge assumptions about where to look for life, it expands them. It shows that even a tiny moon orbiting a gas giant in the shadowed outer solar system can hide an ocean, maintain heat, and erupt material into space, all from beneath a crust of ice.
In 2011, astronomers confirmed the existence of a planet that orbits not one star, but two. Named Kepler-16b, this planet is part of a binary star system about 200 light-years away from Earth in the constellation Cygnus.
What made this discovery especially striking to the public was its resemblance to the fictional world of Tatooine from the Star Wars universe, a desert planet shown with two setting suns in the sky. But Kepler-16b is not science fictionally, it's real.
Kepler-16b is a circumbinary planet, which means it orbits around both stars in the system instead of just one. The two stars themselves, Kepler-16a and Kepler-16b, orbit each other at a distance of about 0.2 astronomical units, AU, with a period of about 41 days.
One is a K-type orange dwarf, and the other a red dwarf. The planet orbits both of them at a distance of about 0.7 AU, closer than Earth is to the Sun, but the system is dimmer and cooler.
So, Kepler-16b is likely a cold gas giant, similar in size and mass to Saturn. The confirmation of Kepler-16b was important because it proved that planets can form and remain stable in binary systems.
Before this discovery, many astronomers believed that the gravitational chaos created by two stars might prevent planets from forming or surviving in stable orbits. Binary stars are common in the galaxy. More than half of all stars may be in binary or multiple star systems.
So understanding whether planets can exist in these systems is critical for estimating how common planets really are. Detecting a planet in a binary system is not easy. The Kepler Space Telescope spotted Kepler-16b using the transit method.
It recorded the tiny regular dips in brightness when the planet passed in front of the stars from Earth's perspective. In this case, it wasn't just the planet transiting the stars.
The stars also periodically eclipsed each other, creating complex light patterns that required careful analysis. The fact that a planet was visible transiting both stars showed it was orbiting them both. The motion of Kepler-16b is stable but complicated.
As the stars orbit each other, they tug on the planet, and the planet, in turn, adjusts its orbit accordingly. The orbital dynamics are governed by three bodies, a classic case of a three-body problem in physics, which is famously difficult to solve. Despite this, Kepler-16b maintains an almost circular orbit with a period of about 229 days. That's comparable to the length of a Venusian year. Conditions on Kepler-16b are likely inhospitable. Since it is a gas giant, it has no solid surface.
The temperature is estimated to be around 100 degrees Celsius, far too cold to support Earth-like life. However, it raises interesting possibilities for exomoons. If Kepler-16b had large moons similar to Jupiter's moon Europa or Saturn's moon Enceladus.
And if those moons had internal heat sources, they could be places where subsurface oceans might exist, even in a cold binary star system. Since the discovery of Kepler-16b, astronomers have found several other circumbinary planets, including Kepler-34b, Kepler-35b, and Kepler-47c, among others.
These planets have different characteristics. Some are gas giants, others are smaller and possibly rocky, but they all orbit two stars. The more of these systems are discovered, the clearer it becomes that planetary formation is flexible and robust, able to operate even in gravitational environments that were once considered unstable.
Simulations now show that circumbinary planets can form in protoplanetary disks that surround both stars, as long as the region where the planet forms is far enough out to avoid destabilizing gravitational interactions. Over time, these planets can migrate inward to their current positions.
Alternatively, they may form in place if the binary stars are relatively close to each other, as is the case with Kepler-16. These findings also reshape our understanding of what star system might look like elsewhere in the galaxy.
For a long time, models of planetary systems were based on our own solar system. One star, several planets, mostly in circular orbits. But binary systems are common, and now we know planets can exist around them.
This adds to the diversity of planetary system architectures and expands the range of environments where we might find habitable worlds.
One interesting consequence of a binary system is the variable sky a planet would have.
On Kepler-16b, the two suns would rise and set at different times, depending on their relative positions. Sometimes they would appear close together, sometimes far apart. There could even be eclipses where one star blocks the other, casting partial shadows across the planet's atmosphere.
The light levels on the planet would change over the course of its orbit, not just because of its distance from the stars, but because of how the two stars move around each other.
These factors would create complex patterns of illumination, a completely different daylight cycle than Earth's. This variability might affect any hypothetical moon's climates or surface conditions, especially if they have atmospheres.
Seasons would be affected not just by axial tilt, but by the movement of the stars and the resulting changes in light and radiation. While we don't have direct data on such moons, models suggest that environments into co-binary systems could be highly dynamic, but not necessarily unstable. Kepler-16b was a landmark discovery because it proved that science fiction scenarios like double sunsets could exist in reality. It also showed that the processes of planet formation are more adaptable than previously thought.
Rather than being rare or exotic, circumbinary planets might be common in the galaxy, especially given how frequent binary stars are. The detection of such planets also demonstrates the precision of instruments like Kepler.
Measuring tiny dips in starlight across multiple moving bodies and disentangling those signals into individual components, stars, planets, orbital periods, requires data accuracy and modeling techniques that were not possible just a few decades ago.
Future telescopes, such as the Nancy Grace Roman Space Telescope or ESA's Plato mission, will likely discover even more circumbinary planets, perhaps including Earth-sized ones, or even planets in the habitable zone of their binary systems.
These discoveries could eventually include rocky planets with atmospheres and surface temperatures that allow liquid water. Kepler-16b remains one of the most iconic exoplanet discoveries of the last 2 decades.
It reminded scientists and the public that the universe is not constrained to the familiar patterns of our own solar system. Planets can orbit one star, 2 stars, or possibly more.
And in some cases, those systems can produce stable, long-lived planets capable of hosting complex environmental conditions. In 2011, astronomers discovered an exoplanet that appeared to reflect almost no light at all.
It was named TRIS-2b, and it orbits a star about 750 light-years away in the constellation Draco. When scientists measured its brightness, they found something unexpected.
The planet was darker than coal, blacker than acrylic paint, and absorbed over 99% of the visible light that hit it. It is one of the darkest known planets in the universe. Most planets reflect at least some portion of the light that strikes them.
Earth reflects about 30% of incoming sunlight due to clouds, oceans, and land surfaces. Even gas giants like Jupiter and Saturn reflect a substantial amount of light, especially because of their thick cloud layers.
But TRUS-tube has a reflectivity or albedo of less than 1%, comparable to charcoal or black acrylic plastic. For an object larger than Jupiter, this level of darkness was unexpected.
Taurus 2b is a hot Jupiter, meaning it is a gas giant that orbits extremely close to its host star. Its orbital distance is only about 5 million kilometers, roughly 30 times closer than Earth is to the Sun.
It completes a full orbit in just 2.47 days, meaning its year is shorter than a weekend.
The proximity to its star heats the planet to over 1.47000 degrees Celsius. At these temperatures, most molecules break apart. Cloud formation becomes difficult, and the atmospheric chemistry changes dramatically.
Astronomers first detected TRES-2b using the transit method, observing the dimming of its star's light as the planet passed in front of it. But its extreme darkness wasn't confirmed until later, when the Kepler Space Telescope collected precise photometric data.
Kepler could not only detect the planet's transit, but also measure the tiny variations in light that occurred as the planet moved behind its star or reflected light toward Earth.
These subtle changes revealed that TARS-2b was not reflecting light the way a planet typically would. One proposed explanation for the planet's darkness is its atmospheric composition. TRS-2b likely has a thick atmosphere of hydrogen and helium, like Jupiter.
But the extreme heat may prevent the formation of reflective clouds like ammonia or water vapor. Instead, its atmosphere may contain light-absorbing molecules such as gaseous sodium, potassium, or titanium oxide.
These substances absorb visible light efficiently, particularly in the red and yellow parts of the spectrum. Additionally, TRES-2d may have a thermally inverted atmosphere, where temperatures increase with altitude. This is the opposite of what happens in many planetary atmospheres, including Earth's troposphere.
Such inversions can occur when high-altitude compounds absorb starlight before it reaches the lower atmosphere. On TRES-2b, this could enhance the absorption of light and prevent even minimal reflection from reaching space.
Despite its darkness, TESS-2b still emits infrared radiation, which is how scientists can study it further. Like a piece of metal heated in a forge, the planet glows faintly in non-visible wavelengths, even though it appears nearly invisible in reflected light.
This thermal emission has allowed researchers to construct models of its temperature profile and atmospheric structure. The fact that TRE-2b is so dark does not mean it's invisible.
Against the blackness of space, even a very dim object can still be detected if its light is carefully analyzed. But in terms of visual appearance, if a person could look at the planet directly, it would appear as a ghostly red glowing orb with almost no visible features.
It would look more like a silhouette or a shadow than a planet. TRES-2b also helps scientists understand atmospheric dynamics under extreme conditions. The planet is likely tidally locked, meaning one side always faces its star, while the other remains in perpetual darkness.
This creates extreme temperature contrast between the day side and night side, with intense winds that move heat and gases between hemispheres. The presence or absence of clouds, haze layers, and absorbing molecules likely varies across the surface, making TAR-2b a dynamic and complex system.
This planet's darkness was a surprise because it contradicts earlier expectations. Before discoveries like this, astronomers assumed that hot Jupiters would reflect significant amounts of light due to thick cloud layers.
But TARS-2b showed that the atmospheric chemistry at high temperatures can suppress reflection almost entirely, turning the planet into a kind of natural black body absorber. It's also worth noting that TRES-2b is not alone.
Other hot Jupiters, such as WASP-12b and HD 9458b, have also been found with low albedos, although none as low as TRES-2b. These findings suggest that low reflectivity may be common in very hot gas giants, especially those orbiting close to their stars.
The exact composition of their atmospheres depends on temperature, stellar radiation, gravity, and other variables. But the trend is clear. Hotter planets can be darker. Understanding these dark exoplanets is important for several reasons.
First, it helps refine planetary atmosphere models, including predictions of how light and heat behave in extreme environments. Second, it aids in interpreting exoplanet observations from instruments like Hubble and James Webb Space Telescope, or JWST.
When astronomers see planets with little or no reflected light, they now have a physical basis to explain it. Finally, it has implications for habitability studies.
While hot Jupiters themselves are inhospitable, knowing how atmospheres absorb and radiate energy can be applied to other types of planets, including Earth-like ones. TRUSC 2b also poses philosophical questions about what a planet should look like.
In our solar system, even the darkest bodies are like Mercury or the Moon reflect some sunlight. They have albedos between 0.1 and 0.12. TRES 2b is almost an exception to planetary appearance itself.
It shows that in some cases, planets do not shine, sparkle, or reflect at all. They simply absorb. The planet's host star, a G-type main sequence star similar to the Sun, allows for relatively easy comparison.
But unlike the familiar planets of our solar system, TRIS 2b reflects less light than any natural object here. If it was replaced by Jupiter in our solar system, it would be nearly invisible to the naked eye, except perhaps as a faint red heat source.
Future telescopes may detect even darker worlds, or may resolve details of TRES 2b's atmosphere to confirm which molecules are responsible for its appearance. JWST, in particular, is capable of studying the infrared spectrum of exoplanet atmospheres in far greater detail than ever before.
If molecular fingerprints of absorbing agents are found, it could solve the mystery of what makes TRUS 2b so incredibly dark. Until then, TRUS 2b remains a fascinating outlier in the catalog of known exoplanets.
A gas giant that doesn't shine, doesn't reflect, and doesn't behave like anything seen in our solar system. It absorbs light almost completely, orbiting its star in silence and near invisibility, like a giant shadow moving through space.
In the vast and complex systems of binary stars, one of the most dramatic and violent interactions happens when a white dwarf, the dense remnant of a dead star, begins to pull material away from its still living companion.
These systems are called cataclysmic variables, and they demonstrate one of the most extreme ways that matter moves in the universe. A white dwarf is the final stage of life for stars that aren't massive enough to end as supernova or black holes.
After such a star, like our Sun, runs out of fuel, it sheds its outer layers in a planetary nebula, leaving behind a hot, dense core about the size of Earth, but with a mass close to that of the Sun.
That object is a white dwarf. It's extremely compact, made mostly of carbon and oxygen, and has no internal fusion but glows due to residual heat for billions of years. On its own, a white dwarf is stable.
But in a binary system where it orbits closely with another star, the dynamics change completely. If the companion star is a mean sequence star, a red giant, or even another white dwarf, and they orbit close enough, gravity can begin to shift the balance.
As the companion star evolves and expands, its outer layers can stretch into a region called the Roche lobe, an imaginary boundary that defines the gravitational limit of each star in a binary system.
Once material crosses this point, it is no longer gravitationally bound to the original star and starts to fall onto the white dwarf. This process is called mass transfer, and it often forms a swirling disk of gas and plasma called an accretion disk around the white dwarf.
The material spirals inward, heating up due to friction and gravitational compression, and can reach temperatures of hundreds of thousands to millions of degrees Kelvin.
The disk becomes so hot that it emits in the ultraviolet and X-ray parts of the spectrum, making these systems observable with space-based telescopes like Chandra on XMM Newton.
One well-known example is SS Cygni, a cataclysmic variable located about 372 light-years away in the constellation. SS Cygni consists of a white dwarf and a companion star that orbits it every 6.6 hours.
Periodically, the system undergoes an outburst, a sudden dramatic increase in brightness caused by instabilities in the accretion disk. As mass builds up, it eventually triggers a temporary but intense burst of energy as material falls more rapidly onto the white dwarf.
These eruptions are visible even from amateur telescopes and have been studied for decades. In more extreme cases, the process can lead to what's known as a nova.
When enough hydrogen-rich material builds up on the surface of the white dwarf, pressure and temperature can become high enough to ignite thermonuclear fusion in a runaway reaction.
This doesn't destroy the white dwarf, but it causes a powerful surface explosion that ejects material into space and increases the system's brightness by a factor of thousands. These novae are not rare. Dozens are observed in the Milky Way each century.
And they are a direct result of one star stealing mass from another. Even more extreme is the case when the white dwarf accumulates too much material and its mass approaches the Chandrasekhar limit, about 1.4 solar masses.
Beyond this threshold, the white dwarf can no longer support its own weight against gravity, and it collapses in a catastrophic thermonuclear explosion called a Type Ia supernova.
Unlike core collapse supernovae, which result from the deaths of massive stars, Type E supernovae are caused by white dwarfs in binary systems undergoing mass transfer.
These explosions are so bright they can outshine entire galaxies and are used as standard candles to measure cosmic distances. The act of one star pulling material from another is not a smooth or symmetrical process.
The material doesn't fall directly from one star to the other. It moves through a complex dance governed by angular momentum, friction, and magnetic fields. The accretion disk that forms can become unstable, warped, or clumpy.
In some cases, powerful magnetic fields on the white dwarf can channel the material along field lines, creating accretion columns and hotspots on the star's surface, which rotate in and out of view and produce periodic X-ray pulses.
In systems where the companion is a red giant, mass transfer can occur through a dense stellar wind. The white dwarf captures this material from the wind, rather than through Roche-Lob overflow. These systems are often called symbiotic binaries.
One famous example is RS Ophiuchi, a symbiotic nova that erupts roughly every 15 years. These explosions are the result of material falling onto the white dwarf and periodically igniting in fusion-driven outbursts.
The recurring nature of these events has made them valuable for studying nova physics over time. The white dwarf itself can undergo changes as it accretes mass. Over time, its surface layers can become enriched with heavier elements.
Some white dwarfs in binaries display metal-rich atmospheres or unusual spectral lines that suggest ongoing accretion. In a few systems, this process leads to the development of super-oft X-ray sources, where the surface temperature becomes hot enough to continuously burn hydrogen in a stable manner.
The long-term evolution of these systems depends on several factors: the mass of the white dwarf, the mass of the companion, their orbital separation, and the rate of mass transfer.
If the white dwarf reaches the Chandrasekhar limit, it will explode in a supernova, destroying itself and potentially disrupting the entire binary system. If it never reaches that mass, it can continue accreting until either the companion is stripped of its envelope or the mass transfer stops due to orbital changes.
These systems can last millions or even billions of years, and their remnants tell the story of stellar interaction. In some cases, if the white dwarf explodes in a Taipei supernova, the companion star may survive and be ejected from the system at high speed.
Astronomers have identified such hypervelocity stars as possible survivors of white dwarf explosions. These stars move through the galaxy at speeds too high to be explained by typical stellar dynamics, and their chemical signatures match predictions for supernova survivors.
The concept of a star stealing material from another star was once purely theoretical, but today, telescopes can directly observe the process in real time in multiple wavelengths. They reveal accretion disks, periodic outbursts, and thermonuclear explosions that result from these interactions.
The systems aren't complex but follow predictable physics: gravitational attraction, conservation of angular momentum, thermodynamics, and they provide valuable laboratories for understanding extreme environments. In the broader picture of cosmic evolution, binary systems involving white dwarfs are not just oddities.
They're essential to the life cycle of stars, to the chemical enrichment of the galaxy, and to the methods astronomers use to measure the expansion of the universe.
From quiet siphoning to violent supernovae, these systems show how stellar remnants continue to play an active role in shaping the cosmos long after their nuclear cores have gone silent.
When astronomers began discovering exoplanets in the mid-1990s, they expected the first planets found would resemble those in our own solar system: rocky worlds near their stars and gas giants further out. Instead, they encountered a class of planets that defied all expectations.
Enormous gas giants, similar in mass to Jupiter, orbiting their stars far closer than Mercury orbits the Sun. These planets were hot, massive, fast-orbiting, and completely foreign to anything seen before. They were named hot Jupiters.
The first confirmed detection of a hot Jupiter was 51 Pegasi b, discovered in 1995. It shocked astronomers by orbiting its host star every 4.2 days, an extremely short year for such a large planet.
Its orbit was just 0.0505 astronomical units, AU, from the star, about 1/8 the distance between Mercury and the Sun. This placed it in an environment of intense stellar radiation, where temperatures could exceed 1,000 to 2,000 degrees Celsius. Yet, despite the heat and proximity, the planet remained intact, bloated and scorching, but stable.
Hot Jupiters are now known to be relatively common among the first exoplanets detected. Their large size and close proximity to their stars made them easier to find using the radial velocity and transit methods.
When a hot Jupiter passes in front of its star, it causes a significant dip in brightness. Likewise, their gravitational tug on their stars produces noticeable wobbles in the star's motion. These characteristics made them the low-hanging fruit of early planet detection missions.
Most hot Jupiters orbit their stars at distances of 0.01 to 0.1 AU, completing full orbits in less than 10 days. Their proximity exposes them to intense radiation, often causing atmospheric heating, expansion, and even loss.
Some of them are so close that their atmospheres are being slowly stripped away by stellar winds, forming comet-like tails of gas tailing behind them. In some cases, ultraviolet radiation ionizes their outer layers, creating visible plasma envelopes around the planet.
These planets are tidally locked, meaning one side always faces the star, while the other remains in permanent night. This creates a severe temperature gradient between the day and night sides, sometimes more than 1,000 degrees difference.
Atmospheric models suggest that supersonic winds, possibly exceeding 5,000 km, redistribute heat across the planet, attempting to balance this thermal contrast. Some hot Jupiters are classified as ultra-hot Jupiters, with temperatures reaching over 2,500 Ka, hot enough to vaporize metals like iron and titanium.
On the hottest of these planets, such as Kelt 9b, molecules can't survive. The heat is so extreme that the atmosphere is composed primarily of atomic ions.
Kelt 9b is heated by a star twice the mass of the Sun and completes one orbit every 1.5 days, with a dayside temperature close to 4,300 C, hotter than some stars.
One key question surrounding hot Jupiters is how they ended up so close to their stars. Gas giants are thought to form in the colder outer regions of a planetary system, beyond what is called the frost line, where water and other volatile compounds can condense into solid ice. In our own solar system, this region lies beyond the orbit of Mars. That's where Jupiter and Saturn formed. But hot Jupiters are well within the frost line, in regions where gas giants shouldn't be able to form. The prevailing explanation is planetary migration.
After forming in the outer parts of the system, these gas giants may have migrated inward over time due to interactions with the protoplanetary disk, gravitational encounters with other planets, or even close passes with other stars.
One common mechanism is disk-driven migration, where the forming planet exchanges angular momentum with the disk, slowly spiraling inward. Another mechanism is high eccentricity migration, where gravitational interactions temporarily put the planet into a highly elliptical orbit, which then circularizes closer to the star due to tidal forces.
The fact that hot Jupiters exist suggests that planetary systems are far more dynamic than once believed. Planetary orbits can evolve dramatically after formation. These migrations can destabilize other orbits, sometimes ejecting smaller planets entirely or pushing them into their stars.
This might explain why many hot Jupiter systems seem to lack nearby smaller planets. The migrating giant cleared them out or prevented them from forming in the first place. Despite their name, hot Jupiters are not exactly like Jupiter.
They often have lower densities caused by inflated atmospheres. Some have radius up to twice that of Jupiter, even if their mass is similar or lower. This inflation is likely due to intense stellar heating and internal processes like tidal dissipation.
Their low density means they are puffier with extended upper atmospheres that can leak into space. The atmospheric composition of hot Jupiters has become a major area of research. Using transmission spectroscopy, scientists analyze the starlight that passes through the planet's atmosphere during transits.
This has revealed the presence of water vapor, sodium, potassium, and even more complex molecules. Some hot Jupiters show evidence of clouds or hazes, while others appear cloud-free, allowing deeper views into their atmospheres.
Observations by the James Webb Space Telescope, JWST, and Hubble Space Telescope are refining these measurements. JWST, with its advanced infrared instruments, can detect minute differences in absorption at various wavelengths, helping to construct temperature maps and atmospheric profiles.
Hearts, the Hawken pauses get a printed now.
In some cases, it may even detect winds, circulation patterns, or day-night chemical differences. Despite their dramatic nature, hot Jupiters are not likely candidates for life. Their extreme temperatures, lack of solid surface, and volatile atmospheric conditions make them inhospitable.
However, they serve as valuable laboratories for studying planet-star interactions, atmospheric escape, and the physical chemistry of high-temperature environments. They also have a role in shaping our understanding of exoplanet system architectures.
Initially considered bizarre outliers, hot Jupiters are now seen as a natural consequence of planetary migration. They reveal the full range of what planetary systems can be: dynamic, chaotic, and unlike anything in our own solar neighborhood.
Their very existence proves that planetary formation is more complex and flexible than originally modeled. From the time they coalesce in a disk of gas and dust to the moment they settled into orbit, planets can undergo violent shifts in position and structure.
Hot Jupiters are evidence that even the largest planets can be dragged into a death spiral, orbiting their stars at distances so close that they're just a few stellar diameters away. Eventually, some hot Jupiters may not survive. Tidal decay could pull them ever closer to their stars, where they might be ripped apart by tidal forces or consumed entirely. This fate may take billions of years, but it's a possibility for the tightest orbiting gas giants. Others may stabilize in their current positions, continuing to endure the intense radiation for eons. Today, hundreds of hot Jupiters are known, and they continue to challenge assumptions. They exist in systems around all types of stars, from sun-like stars to red dwarfs, and even A-type stars. As more exoplanets are discovered, hot Jupiters will likely remain a common and essential class of planet, shaping how we understand the extremes of planetary formation.
In the search for potentially habitable environments beyond Earth, astronomers have long focused on planets within the so-called habitable zone, the region around a star where temperatures allow liquid water to exist on the surface.
But discoveries in our own solar system have shown that liquid water might not always require sunlight. A growing body of evidence suggests that some frozen planets and moons may harbor subsurface oceans hidden beneath thick ice shells.
These challenges are conventional ideas about where life might arise and opens new possibilities for seemingly lifeless frozen worlds. Beyond the asteroid belt, where solar radiation is weak and temperatures plummet, many planetary bodies are covered in solid ice.
These environments appear inert and uninhabitable at first glance, with surface temperatures below 150. But under the right conditions, internal heat can keep water liquid beneath the ice, insulated by kilometers of frozen crust. This phenomenon is not just theoretical.
In our own solar system, moons like Europa, Ganymede, Titan, and Enceladus are believed to have internal oceans, and now scientists suspect that some exoplanets, entire frozen worlds, may have similar structures.
One promising candidate is Ogle 2005 BLG 399, an exoplanet discovered through gravitational microlensing in 2005. Located roughly 21,000 light-years away in the constellation Scorpius, it is about 5.5 times the mass of Earth and orbits a red dwarf star at a distance that makes it incredibly cold, with an estimated surface temperatures around 200 Wald.
That's colder than Pluto. At first glance, the planet appears to be a frozen wasteland well beyond the limits of habitability. However, models suggest that its internal structure might allow for a subsurface ocean warmed not by starlight, but by residual heat from its formation and radioactive decay in the core.
The idea is that a thick, icy crust insulates the interior. As heat radiates outward from the planet's center, it melts the inner layers of the ice, creating a layer of liquid water beneath the surface.
Similar to Europa and Ganymede, this water would be trapped between the planet's rocky mantle and its ice shell. On Earth, we see a comparable effect in Antarctica's subglacial lakes.
Vast pockets of liquid water sealed beneath kilometers of ice, untouched by the atmosphere for millennia, but still maintained in a liquid state by geothermal heat.
On Ogle 2005 BLG 39LB, the outer ice layer may be tens to hundreds of kilometers thick, but it could still trap enough heat to keep water in a liquid state below.
If correct, this would mean that the planet has the conditions for a stable, long-lived subsurface ocean, possibly for billions of years. The idea that liquid water can exist so far from a star expands our definition of habitability beyond the classic habitable zone and opens up the possibility that many more planets could support lifelike conditions deep below their frozen surfaces.
The key is internal heat. Even a frozen planet that receives very little stellar radiation can maintain a warm interior if its core contains enough radioactive elements such as uranium, thorium, and potassium.
As these elements decay, they release heat, which can melt ice from below. Tidal forces, gravitational interactions between the planet and its star or nearby moons, in the case of icy satellites, can also contribute heat by causing friction in the interior.
On Ogle 2005 BLG 390LB, the exact heating mechanisms are uncertain, but thermal modeling suggests that the energy may be sufficient to sustain a deep hidden ocean for billions of years.
Well, this particular planet is too far away to study in detail with current telescopes. Its discovery has major implications. If one frozen planet can sustain an internal ocean, then many others likely can too.
There are hundreds of billions of red dwarf stars in the galaxy, many of which could have cold super-Earths or mini-Neptunes orbiting them. Even if these planets are outside the traditional habitable zone, they might still support subsurface oceans beneath their frozen crusts.
This would dramatically increase the number of worlds that could potentially support microbial life. Closer to home, frozen ocean worlds like Europa and Enceladus serve as analogs for what might be happening on planets like Ogle 2005 BLG 390LB.
Data from spacecraft missions like Galileo, Cassini, and the upcoming Europa Clipper have shown that thick ice layers can conceal active subsurface oceans. In some cases, plumes of water vapor have even been observed erupting into space, giving direct evidence of liquid reservoirs beneath the ice.
If such activity occurs on distant exoplanets, it may not be visible with today's instruments, but it could one day be detectable with next-generation telescopes. What makes these frozen planets particularly interesting is their stability.
Because they don't rely on sunlight to maintain liquid water, they aren't affected by changes in stellar luminosity or radiation. While a star like the Sun will eventually expand and die, changing the habitability of its planets, a subsurface ocean powered by internal heat could remain stable for far longer.
This makes frozen ocean planets potential refugees for life, possibly sustaining biology in hidden environments long after surface conditions have become uninhabitable. Of course, life in such oceans would face major challenges.
With no light,
any life would need to rely on chemosynthesis, drawing energy from chemical reactions rather than photosynthesis. On Earth, deep-sea organisms thrive around hydrothermal vents using a similar process, converting hydrogen sulfide or methane into energy. If frozen ocean planets have rocky seafloors and the right chemical ingredients, similar abiotic energy sources could support simple life forms, even in total darkness. Detecting subsurface oceans on exoplanets is extremely difficult.
Unlike transiting planets, which reveal atmospheric data as they pass in front of their stars, frozen super-Earths may be distant, dim, and lacking transits altogether.
However, future telescopes, like the James Webb Space Telescope, LUVOIR, or ELT, Extremely Large Telescope, could be sensitive enough to detect indirect signs, gravitational effects, infrared thermal emissions, or even spectral hints of plume activity if present.
Ultimately, OGLE 2005 BLG 390 LB represents a new category of planetary body, one that is cold on the outside but possibly warm on the inside. It challenges our ideals about what a dead world looks like.
Just because a planet is frozen doesn't mean it's inert. It could be active with churning internal heat, circulating oceans, and perhaps even the chemical building blocks of life, all sealed beneath a thick, icy lid.
These kinds of discoveries suggest that life might not need sunlight at all. It might just need liquid water, some energy source, and the right chemistry.
If so, then the galaxy may be teeming with hidden oases, entire worlds that look like frozen wastelands from space, but that shelter warm, dark oceans below. In our solar system, Earth's seasons are caused by the 23.5-degree tilt of its rotational axis.
As Earth orbits the Sun over the course of a year, different parts of the planet receive more or less sunlight, producing the familiar pattern of spring, summer, autumn, and winter.
On Earth, a full cycle of seasons takes 12 months, but that's far from universal. On other worlds, especially those with extreme tilts or long orbits, seasons can last not months, but decades. The best-known example is Uranus, the seventh planet from the Sun.
Uranus is a gas giant with a peculiar axial tilt of 98 degrees, meaning it essentially rotates on its side. Instead of spinning like a top upright on a table, Uranus spins more like a rolling ball.
This unusual orientation causes the planet to experience some of the most extreme seasonal changes in the solar system. Each pole spends 42 Earth years in continuous sunlight, followed by 42 years of darkness, completing a full orbit around the Sun every 84 Earth years.
When a planet has an axial tilt close to 90 degrees, the orientation of its sunlight changes dramatically over the course of its orbit. For Uranus, during the summer solstice in its northern hemisphere, the North Pole points almost directly at the Sun.
That region of the planet experiences continuous daylight, while the southern hemisphere is plunged into long, cold darkness. Half an orbit later, the roles reverse. These result in seasons that last over 4 decades, with the poles alternating between endless summer and polar night.
The effects of these long seasons are profound, though not fully understood. Unlike Earth, Uranus has a thick hydrogen-helium atmosphere, no solid surface, and limited visible weather compared to its neighbor, Neptune. For a long time, Uranus was considered a relatively featureless planet,
But in recent decades, astronomers using Hubble and powerful ground-based telescopes have observed atmospheric changes, cloud formation, wind patterns, and storm activity that appeared to be linked to Uranus's seasonal cycle.
When Uranus approaches one of its solstices, solar energy is concentrated on one hemisphere for decades at a time. This may drive large-scale changes in the atmosphere. Though the planet's distance from the Sun, nearly 3 billion kilometers, means the energy input is weak.
Still, over time, the sunlight accumulates and can lead to stratified heating, slowly warming the upper layers of the hemisphere in sunlight while the opposite side cools in darkness.
Because the seasons progress so slowly, these temperature changes can lag the temperatures by years or even decades. The equatorial regions of Uranus receive less dramatic changes in sunlight over the course of the orbit, but they are too affected by the shifting temperature and pressure systems.
Wind patterns can change direction, cloud belts can shift in latitude, and storms can appear where none were observed before. Some of the bright atmospheric features detected by Hubble, including massive storms, are thought to be linked to seasonal transitions, especially when the planet moves past an equinox and the balance of sunlight shifts hemispheres.
The extreme axial tilt of Uranus is likely the result of a catastrophic collision early in its history. Simulations suggest that Uranus may have been struck by a large protoplanet, possibly the size of Earth, which knocked it onto its side.
This would also explain why Uranus has a relatively low internal heat flux compared to other gas giants. Unlike Jupiter or Neptune, which emit more heat than they receive from the Sun, Uranus has a surprisingly cold interior.
One theory is that the impact disrupted its core or left it with a composition that prevents efficient heat transport. The slow, dramatic seasons of Uranus are not unique to it alone.
Exoplanets orbiting other stars may also experience long seasons, depending on their tilt and orbital characteristics. Some planets orbit in highly elliptical paths, meaning they experience huge temperature differences between perihelion, closest approach to the star, and aphelion, farthest distance.
If these planets also have a strong axial tilt, they could undergo climate regimes that last centuries, alternating between prolonged warm and cold periods. For instance, a planet with an Earth-like tilt but long orbital period, such as a Jupiterized world far from its host star, might experience seasons that last tens or even hundreds of Earth years.
In such environments, a summer might mean gradual warming over 30 to 50 years, followed by equally long winters. Any life or atmosphere on such a planet would need to adapt to very slow large-scale changes, unlike the rapid seasonal turnover we're used to on Earth.
In theory, tilt and orbit can create any combination of season lengths. A planet with no axial tilt would have no seasons at all. A planet with an extreme tilt, like Uranus, or even beyond, would have exaggerated polar heating and cooling cycles.
Combine this with a long orbit, and the seasons could stretch across geological timescales. Long seasons would also affect habitability. For any potential life on such a world, the slow rhythm of heating and cooling would pose major challenges. Plant life, for example, would need to survive decades of cold and darkness, or develop some form of metabolic dormancy that could last through the cycle. Animal life, if it existed, might migrate globally, follow thermal zones, or even hibernate for years at a time.
Back on Uranus, the long seasons pose questions for future exploration. While Voyager 2 flew by the planet in 1986, capturing the only close-up images we've ever had, no dedicated mission has yet visited the system again.
Scientists are eager to return, not just to study the planet's extreme tilt and odd seasons, but also its complex ring system, icy moons, and peculiar magnetic field, which is tilted 59 degrees from the planet's rotation axis and offset from its center.
The next solstice on Uranus will occur in 2028, and it will take until 2069 for the following equinox. Capturing seasonal changes in real time requires long-term monitoring and investment in spacecraft and telescopes capable of watching subtle shifts over decades.
But doing so could unlock key insights about climate stability, atmospheric dynamics, and the impact of axial tilt on planetary systems, not just for Uranus, but for distant exoplanets that may be experiencing similar patterns.
In summary, Uranus serves as a striking reminder that planetary behavior can be vastly different from what we consider normal. A season does not have to be measured in months. On some worlds, it can stretch across a human lifetime.
It can bring prolonged extremes of sunlight and darkness, reshape atmospheric systems, and challenge the definition of habitability itself. These 40-year-long seasons are not a fluke. They're a natural consequence of orbital mechanics and axial geometry, and they may be common across the universe.
In 2007, astronomers using NASA's Spitzer Space Telescope made a startling observation. They were studying a gas giant exoplanet called HD 89733b. located about 64 light-years away in the constellation Vulpecula.
As one of the closest and most intensely studied hot Jupiters, this planet had already stood out for its extreme temperatures and bloated atmosphere. But now, scientists have discovered something even more dramatic.
Winds blasting through its atmosphere at speeds exceeding 8,700 kilometers an hour, over 7 times the speed of sound on Earth. HD H9733b is a hot Jupiter, a gas giant roughly 1.1 times the mass of Jupiter and slightly larger in size.
It orbits its host star at a distance of just 0.03 to 03 AU, or about 4.5 million kilometers, completing a full orbit every 2.2 Earth days.
At this distance, the planet is exposed to intense radiation, heating its atmosphere to temperatures around 1200 degrees Celsius to 2000 Kelvin on the day side.
This enormous influx of stellar energy drives powerful winds, creating a dynamic and violent climate unlike anything seen in the solar system. The discovery of supersonic winds came through a technique called phase curve analysis.
By continuously monitoring the planet as it orbited its star, astronomers could measure the infrared light emitted by different sides of the planet at different phases.
Normally, you would expect the hottest part of the atmosphere to be directly under the star, where it receives the most light. But on HD 1899733b, the hottest region was offset eastward away from the substellar point. This indicated that winds were transporting heat across the planet's surface, fast enough to shift the thermal hotspot by tens of degrees in longitude. The wind speeds were calculated based on how much the hot spot was displaced and the timing of heat redistribution.
The result, winds reaching 500 to 400 miles per hour or Mach 7, blowing from the planet's day side to its night side around the equator. These are among the fastest winds ever measured on any planet.
And they don't just move the air. They shape the entire climate of the world. HD 8973b is tidally locked, meaning one side of the planet always faces the star, while the other remains in permanent night. This configuration creates an extreme energy imbalance.
One hemisphere is constantly being cooked by radiation while the other is shrouded in darkness. The only way to balance the temperature is through atmospheric circulation. And that's where the supersonic winds come in.
Driven by the intense heating and rapid rotation, they whip around the planet in massive jet streams that transfer energy from day to night. The winds are part of a complex pattern of circulation that includes vertical mixing, vortexes, and possibly stratospheric airflows.
Models suggest that in the upper atmosphere, these winds are primarily eastward, while deeper layers may have more complex, possibly even counter-rotating currents. The massive scale of the atmosphere, combined with the absence of solid surface friction, allows these jet streams to persist without being slowed down the way they would be on Earth.
Later observations using Hubble and ground-based spectrographs helped confirm the wind speed measurements by looking at the Doppler shift in the planet's atmosphere. When molecules in the atmosphere move toward or away from us, their spectral lines shift slightly, and these shifts can be used to measure wind speeds directly.
In HD 89733b's case, the results supported earlier findings. Its atmosphere was indeed moving at blistering velocities. These discoveries not only revealed the violent nature of this specific planet, but also changed our understanding of weather on exoplanets.
Unlike the relatively gentle jet streams on Earth, which peak at about 400 kilometers an hour, gas giants like HD 149733b experience continuous global-scale hurricanes that never stop.
There's no land to break up the flow, no oceans to absorb heat, and no seasons to moderate the climate. The winds blow without interruption, driven by the unyielding pressure of their star. HD 89733b is not alone.
Other hot Jupiters, such as WASP-43b and HATP-7b, have shown similar, sometimes even more extreme wind and temperature patterns. In one case, wind speeds were so high that clouds of vaporized metal may have been transported from one side of the planet to the other.
On WASP-76b, observations suggest that iron condenses on the night side and rains down, only to be vaporized again as it's carried back to the day side, a kind of metallic weather driven entirely by these planet-spanning winds.
The study of these extreme winds is more than just a curiosity. Understanding how heat and air move in such hostile environments helps astronomers refine climate models and interpret atmospheric spectra.
When light from a star passes through a planet's atmosphere, the winds can alter the absorption lines and confuse the data. Accounting for wind patterns improves the accuracy of chemical composition readings and temperature maps.
HD 189733b is also scientifically important because of its relative proximity to Earth and the brightness of its host star. These factors make it an ideal target for telescopes like the James Webb Space Telescope, which has the resolution and sensitivity to observe subtle shifts in atmospheric chemistry and motion.
JWST will likely produce even more detailed wind profiles, possibly mapping how winds change with altitude, temperature, or time of day. One unexpected feature of HD 890733b is its deep blue color, not from water or oceans, but from scattering in its upper atmosphere and the possible presence of silicone particles. These particles could be the result of high-altitude clouds made from vaporized rock, which form and dissipate in response to wind and heat. The blue hue is deceptive.
It suggests a tranquil ocean world, but in reality, it's a hellish gas giant where winds rage at speeds faster than sound and temperatures are hot enough to melt metal. No spacecraft has ever visited HD 89733b.
It's too far and beyond the reach of our current propulsion systems, but it remains one of the most well-characterized exoplanets we've studied. Its extreme winds, temperature shifts, and atmospheric chemistry make it a benchmark for understanding hot Jupiters and a vivid example of how alien weather can be.
On Earth, hurricanes and jet streams are measured in hundreds of kilometers an hour. On this distant planet, they reach thousands. The air itself becomes a destructive force, carrying heat, chemicals, and particles in loops around the globe at relentless, unimaginable speed.
Most stars, including our Sun, are roughly spherical, the natural shape that results when gravity pulls equally from all directions. But under extreme conditions, that symmetry can break.
When a star spins fast enough, centrifugal force begins to counter gravity at the equator, stretching the star into an oblate shape, flattened at the poles and bulging at the equator.
In rare cases, the effect is so extreme that the star becomes visibly distorted, taking on a shape that resembles a peanut, a flattened disk, or even a barbell in space.
One of the most well-known examples is Acuna, the brightest star in the constellation Eridanus and the 10th brightest star in the night sky. Located about 140 light-years from Earth, Achernar is a B-type star, hot, blue, and massive, with surface temperatures over 15,000 degrees centigrade, several times hotter than the Sun.
But what makes it extraordinary is not its brightness or heat, it's its shape. Ashen spins at an estimated rotational velocity of over 250 kilometers per second at its equator. This is more than 15 times faster than the Sun's equatorial rotation.
The result of this rapid spin is dramatic. Achernar is not even close to spherical. Measurements show that its equatorial diameter is about 50% larger than its polar diameter. If Earth were to spin at a similar rate, its equator would bulge out.
So much that the planet would resemble a discus and likely tear itself apart. The forces at play are simple in theory, but extreme in practice. A spinning object generates centrifugal force, which pushes outward from the axis of rotation.
At a star's equator, this force acts against gravity. The faster the spin, the stronger the centrifugal force, and the more the star's outer layers are pulled outward. At a certain point, the balance tips.
The equator expands while the poles remain relatively compressed, producing a flattened, distorted structure. Achernar is not unique in this regard. Several stars, particularly B stars, a class of rapidly rotating B-type stars with emission lines, show significant oblateness.
Some even develop equatorial disks of gas formed when material at the equator is ejected due to the spin rate approaching the star's breakup velocity, the speed at which centrifugal force would completely overcome gravity and cause the star to fly apart.
Achernar isn't quite at that limit, but it's close. Astronomers have directly measured Achernar's shape using interferometry, a technique that combines the light from multiple telescopes to create images with much higher resolution than a single telescope could achieve.
These observations, particularly from the Very Large Telescope Interferometer, VLTI, revealed Achernar's peanut-like shape and confirmed that its equator is significantly extended relative to its poles. The star's extreme shape also affects its surface temperature and brightness distribution, a phenomenon known as gravity darkening.
Because gravity is weaker at the equator due to centrifugal force,
The outer layers of the star are less compressed there. This means that the equator is cooler and dimmer than the poles.
In Achernar's case, the poles may be thousands of degrees hotter than the equator, creating a stark contrast in temperature and brightness across the surface. If you were close enough to see it directly, Achernar would not shine uniformly.
It would appear brighter at the top and bottom, and dimmer along the bulging equator. This also means that measuring Achenar's overall temperature, or luminosity, is more complex than for a spherical star.
Depending on the angle from which we observe it, we may be looking more at the hot poles or the cooler equator, which affects how we interpret the star's spectral data.
Understanding this differential heating is important not just for Achernar, but for all fast-spinning stars, as it influences their evolution and observed properties. Rapid rotation also affects a star's lifespan and evolution.
Stars that rotate quickly can experience internal mixing. Elements from the core are transported to outer layers and vice versa. This can extend the star's time on the main sequence by delaying hydrogen depletion in the core. However, the same rotation can cause mass loss, especially at the equator, where material may be thrown off into space. Over time, this can alter the star's mass, angular momentum, and chemical makeup.
Some of the most extreme rotational distortions may occur in binary systems, where tidal forces and past interactions cause stars to spin faster than they otherwise would. In some cases, a star may accrete material from a companion, gaining angular momentum in the process.
This can spin it up to near breakup velocity. In rare situations, two stars may even merge, producing a single, fast-spinning object with an unusually shaped and chaotic outer structure.
The distorted shape of fast-spinning stars also affects their pulsation modes, the way they oscillate internally. These oscillations are important tools in astroseismology, the study of stellar interiors based on surface vibrations. A spherical star has symmetrical modes of pulsation, but an oblate or peanut-shaped star exhibits complex asymmetrical oscillations which make modeling more difficult but also provide more detailed information. For planets orbiting such stars, the consequences are significant.
The gravitational field of a distorted star is not uniform, which can affect the stability and shape of planetary orbits. Furthermore, the stellar radiation a planet receives may vary depending on its orbit.
A planet that passes near the hot poles will be irradiated more than one that orbits closer to the cold equator. These effects could impact atmospheric chemistry, potential habitability, and climate cycles on any nearby worlds.
Though Achernar is too massive and hot to host habitable planets, its peculiar shape makes it an ideal natural laboratory for studying stellar physics at extremes.
Future missions such as interferometric space observatories could eventually image more stars with similar shapes and help quantify how widespread these distortions are across the galaxy.
In theoretical astrophysics, simulations have shown that stars spinning close to their breakup velocity could become extremely oblate, with equators that puff out so much they resemble toroids or disks. In some cases, this distortion can be temporary, occurring during a phase of rapid mass accretion or stellar merging, and may settle down over time. In others, it may persist for millions of years, gradually shedding angular momentum through stellar winds or magnetic braking. Ultimately, stars like Achernar remind us that not all stars are spherical, and that the laws of physics, when pushed to their extremes, can sculpt even stars into unexpected shapes. Rotation, gravity, radiation, and fluid dynamics combine to form objects that are not just luminous, but structurally complex.
In a universe where we often picture stars as perfect glowing spheres, the reality is more chaotic and far more interesting.
Black holes are extreme objects, so dense and compact that not even light can escape from within their event horizons. But their gravitational effects stretch far beyond their invisible boundaries.
One of the most mind-bending consequences of black holes is something predicted by Einstein's theory of general relativity: time dilation. Near a black hole, time doesn't flow the same way it does elsewhere. As you get closer to the event horizon, time itself slows down.
And just outside it, it nearly stops. Time dilation is not science fiction. It's a confirmed phenomenon rooted in Einstein's understanding of gravity. In simple terms, the stronger the gravitational field, the more slowly time passes. On Earth, this effect is minuscule.
Atomic clocks placed at sea level tick slightly slower than those on mountaintops, but the difference is measured in nanoseconds. Near a black hole, the effect becomes extreme.
To understand this, you first need to grasp the concept of the event horizon, the boundary around a black hole beyond which nothing can escape, not even light.
For a non-rotating black hole, this is defined by the Schwartz radius, which depends only on the black hole's mass. As you approach this radius, the curvature of space-time increases sharply. Space becomes compressed, and time becomes stretched. Imagine a spacecraft approaching a black hole.
To a distant observer, watching from a safe distance, the ship appears to slow down as it gets closer to the event horizon. Its clocks seem to tick more slowly.
Its movements stretch out, and as it reaches the horizon, it appears to freeze in place, never actually falling in. But from the perspective of someone on the spacecraft, time feels normal. They continue to tick forward at 1 second per second.
The key difference is that time is passing much more slowly for them compared to the rest of the universe. This effect is not just theoretical.
Astronomers have detected gravitational time dilation near massive neutron stars, where light emitted from the surface appears redshifted due to time passing more slowly in the star's intense gravitational field. The same principle applies near black holes, but on a much greater scale.
Let's use a hypothetical example. If you were to orbit a supermassive black hole like the one at the center of our galaxy, Sagittarius A, which has a mass of about 4 million suns, time dilation would become significant.
If you stayed in a stable orbit just outside the event horizon for a few hours, then returned to Earth, you might find that years or even decades had passed for everyone else. This is not a science fiction scenario.
It's a consequence of general relativity and has been modeled mathematically with precise predictions. In 2014, the movie Interstellar popularized this concept with a fictional planet orbiting close to a supermassive black hole named Gargantua.
The movie claimed that 1 hour on the planet equaled 7 years outside. While the specifics were exaggerated, the idea was scientifically grounded. A real planet couldn't survive that close without being torn apart by tidal forces unless the black hole was rotating rapidly, which reduces the size of the event horizon and allows closer, stable orbits.
But the core concept that time can pass differently based on gravity is entirely accurate. Mathematically, time dilation near a black hole can be described using the Schwartz metric.
The closer you get to the event horizon, the more the denominator in the time dilation equation approaches zero, and the more slowly time passes for you. Relative to a distant observer just outside the event horizon, time would still move, but incredibly slowly.
This means that, in theory, someone could sit in that region and watch the universe race ahead, stars being born and dying, galaxies merging, cosmic time accelerating and fast forward. Of course, getting that close is dangerous.
The region just outside the event horizon is filled with intense radiation, gravitational tidal forces, and unpredictable space-time curvature. For small black holes, these forces would tear apart any object, a process called spaghettification, where objects are stretched and compressed by tidal gravitation.
But around larger black holes, like supermassive ones, the tidal forces at the event horizon are actually weaker due to the larger radius. That makes the extreme time dilation more survivable, at least in theory. This also leads to a profound implication.
For anything falling into a black hole, the universe outside will appear to speed up. A person crossing the event horizon would not notice any change in their own time flow.
But if they could look out, they might see stars spinning, galaxies evolving, and cosmic history playing out in fast forward. In the final moments before crossing the event horizon, external time would accelerate so much that the entire future of the universe could unfold in what appears to be seconds.
Time dilation also plays a role in the physics of black holes themselves. As matter falls into the black hole, from an outside point of view, it never quite crosses the event horizon.
Instead, it appears to slow, fade, and become redshifted, blending into the black hole shadow. This has implications for information loss, Hawking radiation, and the debate over whether black holes destroy information or store it on the event horizon.
In real astrophysical environments, time dilation can also affect objects in accretion disks around black holes. These disks, made of superheated gas spiraling toward the event horizon, are some of the brightest objects in the universe.
As gas orbits faster and closer to the black hole, it experiences relativistic time dilation. This must be accounted for in models of the disk's brightness, temperature, and X-ray emissions.
In 2019, the Event Horizon Telescope produced the first real image of a black hole shadow in the galaxy M87. The dark center of the image, surrounded by a bright ring of radiation, represents the point beyond which light cannot escape.
That bright ring contains radiation from material orbiting near the speed of light in a region where time dilation is already extreme. These are not just static images. These are snapshots of space-time under pressure, shaped by gravity so intense that even time itself distorts.
Even on Earth, the principles of gravitational time dilation have practical applications. The GPS satellites that orbit the planet must account for both special relativity, because they are moving quickly, and general relativity, because they're farther from Earth's gravity well.
Without correcting for time dilation, GPS systems would quickly become inaccurate by several kilometers per day. This shows that even small time differences, imperceptible to humans, have real consequences in technology. But near a black hole, these effects are no longer subtle. They are dramatic.
Time slows, space warps, and the universe outside seems to accelerate. From far away, someone falling toward a black hole appears frozen in time. From up close, the rest of the universe appears to sprint forward. It's not just a trick of perception. It's the real warping of space and time caused by gravity itself. Galaxies are typically defined by the stars they contain. The Milky Way, for example, forms new stars at a rate of about 1 or 2 per year.
Star formation is considered a key part of a galaxy's life cycle, a sign of ongoing activity and internal motion. But astronomers have discovered galaxies that challenge that idea completely. These galaxies no longer form stars, yet they continue to glow across the electromagnetic spectrum.
One notable example is MAX 2020, a massive compact galaxy located more than 10 billion light-years away, where no stars are forming, and yet it remains bright and visible. MAX 2020 belongs to a rare category known as quiescent galaxies.
These are galaxies that have, for reasons still under investigation, shut down their star formation. Unlike starburst galaxies, which rapidly convert gas into stars, or spiral galaxies like ours, which maintain a steady star formation rate, quiescent galaxies are essentially in cosmic retirement.
Their gas has been consumed, expelled, or heated to the point where it can no longer cool and condense to form new stars. Still, these galaxies are not invisible.
They emit light, not because of new stars, but because of the combined glow of the old stars that remain. MAX 20 Torn Coins North is especially puzzling because of its age and distance.
It's seen as it was just 3 billion years after the Big Bang, yet already it had stopped making new stars. In other words, this galaxy formed quickly, built up its stellar mass early, and then became quiescent far earlier than the models had predicted.
This contradicts the previous assumption that early galaxies were uniformly chaotic, dusty, and constantly forming stars. Some, like MAX 2280 E1, had already evolved beyond that stage, becoming stable and quiet.
Despite being dormant in terms of star birth, MAX 2291-1 still glows brightly in infrared and optical wavelengths. That's because it's packed with older evolved stars, mostly red and yellow giants, that emit steady light as they age.
These stars don't flare, pulse, or explode at the same rate as younger, massive stars, but they still produce a consistent, detectable brightness. The galaxy's glow is the aggregate result of hundreds of billions of these aging stars shining steadily without replenishment.
Its shape also adds to the mystery. Unlike many quiescent galaxies, which tend to be elliptical and disordered, MAX 2129-1 appears to have a disc-like structure, similar to spiral galaxies, but without the spiral arms or dust lanes associated with star formation.
This suggests it was once a spiral galaxy that simply shut down. How a galaxy can retain such a structure without the continued dynamism of star-forming regions is still unclear.
Most models suggest that spiral galaxies need the movement of gas and the creation of new stars to maintain their form. So why did Max J. Kirimgel 2829.1 stop forming stars? Several mechanisms have been proposed. One explanation is gas depletion. The galaxy may have simply used up all its available cold gas, the raw material needed to make stars. Once a galaxy runs out of hydrogen, star formation grinds to a halt.
However, this doesn't fully explain how such a large galaxy forming so early in the universe could burn through or lose all its gas so quickly. Another possibility is feedback from active galactic nuclei, AGN.
Many massive galaxies host supermassive black holes at their centers.
When these black holes feed on gas and dust, they can release powerful jets of energy that heat or blow away surrounding material.
This feedback can suppress star formation by preventing the gas from cooling and condensing. If MOX 2029 once hosted in AGN, it may have ejected or heated its gas enough to permanently halt new star births. A third idea involves environmental quenching.
Galaxies that live in dense clusters often interact with their neighbors, or the intracluster medium. These interactions can strip away gas, disrupt internal motion, or cut off a galaxy's supply of new material.
Over time, these processes can cause even a healthy gas-rich galaxy to become sterile. If Mach 1729-1 resides in a high-density environment, as many early quiescent galaxies do, this could have contributed to its inactivity.
Interestingly, the fact that Max 2129-1 still glows even without any new stars forming tells us something important about the lifespan of lightning galaxies. Stars can live for billions of years. Red dwarfs in particular can burn steadily for trillions of years.
So even if a galaxy stops making new stars, its existing population will continue shining for a long time. The light we see from Max 2129-1 today is a mixture of intermediate mass stars nearing the ends of their lives and low mass stars that will outlive the galaxy's active phase by unimaginable spans of time.
But its future is limited. Without new star formation, a galaxy's light will slowly fade. The massive stars die first in supernova explosions or quiet transitions into white dwarfs. Over billions of years, the remaining stars will exhaust their fuel. The galaxy will grow dimmer, redder, and eventually invisible. It will still contain stars and mass, but no active light. It becomes a red and dead galaxy, visible only in the infrared, with no sign of the bustling energy it once held.
Max 21-1 isn't the only example. Zombies, galaxies, a nickname for glowing but dormant galaxies, have been identified at different stages of the universe. Some are relatively close, showing what our own Milky Way might look like billions of years from now.
Others are ancient, showing that galaxy quenching is not a recent phenomenon. In fact, the early quenching of galaxies like Max 2129-1 suggests that galactic evolution is far more rapid and diverse than previously thought. The implications for cosmology are significant.
These galaxies help astronomers test models of dark matter, halos, feedback processes, and galaxy morphology. They reveal that galaxies can shut down at various points in cosmic history, and they help refine our understanding of how different environments and internal dynamics affect galactic life cycles. Technologically, studying these galaxies pushes the limits of our instruments. Observing quiescent galaxies at high redshifts requires sensitive infrared detectors, like those aboard the James Webb Space Telescope, JWST.
With its ability to peer into the distant past, JWST is expected to identify many more ancient glowing galaxies that are no longer alive, mapping their distribution and revealing the timing and mechanics of galactic quenching.
In short, Max 2029-1 is a reminder that light doesn't always mean life, at least not in the ongoing sense. A galaxy can glow brightly not because it is active, but because it is still coasting on the energy of its earlier days.
It's a fossil from a time when star formation was active, preserved in the light of stars that refuse, for now, to go dark. In cosmology, there's a rule known as the cosmological principle.
The assumption that on large enough scales, the universe is homogeneous and isotropic.
That means matter should be evenly distributed when you zoom out far enough. Galaxies and galaxy clusters may form filaments, walls, and voids, but eventually these fluctuations should average out.
According to this principle, no structure should be larger than about 1.2 billion light-years across. But in 2013, astronomers discovered something that directly challenges that limit, a massive structure called the Hercules Corona Borealis Great Wall, stretching an estimated 10 billion light-years across.
This discovery came as a surprise. The structure wasn't detected by looking at galaxies or galaxy clusters directly, but by analyzing the locations of gamma-ray bursts, GRBs, incredibly energetic explosions that occur when massive stars collapse or neutron stars merge. GRBs are among the brightest events in the universe, often visible from billions of light-years away. Because they are short-lived and very luminous, they serve as excellent markers of star-forming regions and distant galaxies.
While mapping the locations of GRBs detected by the Swift Gamma-Ray Burst mission, researchers noticed an unusual clustering of bursts in the direction of the constellations Hercules and Corona Borealis.
Statistical analysis revealed that these GRBs were not randomly distributed, but instead concentrated in a pattern suggesting a colossal cosmic structure. The estimated size of this structure, if it indeed represents a physical entity, was over 10 billion light-year across.
To put that in perspective, the Milky Way is 100,000 light-years wide. The local group of galaxies spans a few million light-years. The Sloan Great Wall, previously thought to be one of the largest structures, is about 1.4 million light-years across.
The Hercules Corona Borealis Great Wall is 7 times larger than that. It's so big that light would take most of the universe's current age just to travel from one end to the other. If confirmed, such a structure would violate the cosmological principle.
According to standard models of the universe, density fluctuations in the early universe caused by quantum variations during cosmic inflation grew over time into the large-scale structures we see today: filaments, galaxy walls, and superclusters.
But those fluctuations should smooth out beyond a certain scale. Something as large as this Great Wall is not supposed to exist. That's why it's controversial. Not all cosmologists accept the structure as real.
Some argue that it may be a statistical fluke, a random clustering of GRBs that appear structured due to limited data. Others suggest that the clustering could be an observational artifact, the result of biases in how GRBs are detected or how distances are calculated.
GRBs are rare events, and the methods used to determine their redshift can introduce errors, especially when sample sizes are small. Still, the clustering appears consistent across multiple datasets.
Follow-up studies using independent analyses have supported the initial findings, strengthening the case that this is a genuine anomaly in the large-scale structure of the universe. If it's real, it forces a reconsideration of several key ideas in cosmology.
One possibility is that the cosmological principle might be an approximation valid only up to a point. The universe may not be fully homogeneous even at the largest scales.
If that's the case, then new models of cosmic evolution are needed, those that allow for regional overdensities or anisotropies on larger than expected scales. This could require changes to inflation theory, dark matter models, or the geometry of space itself.
Another implication is that we may not yet fully understand the relationship between GRBs and cosmic structure. If GRBs preferentially occur in certain types of galaxies or environments, their clustering could reflect more about their hosts than about the universe's structure as a whole.
However, given how spread out and luminous these events are,
the clustering still suggests a massive underlying framework of matter. Even if it's composed of loosely connected filaments and voids, the idea of cosmic walls and filaments is not new.
Surveys like the Sloan Digital Sky Survey, SDSS, and the two-dimensional Galaxy Redshift Survey have revealed a cosmic web, a vast network of interconnected superclusters and voids stretching hundreds of millions of light-years.
But each of these structures, like the CFA2 Great Wall, the Sloan Great Wall, or the Boot Void, remains within the bounds predicted by cosmological theory. The Hercules Corona Borealis Great Wall exceeds those bounds dramatically.
One explanation, if the structure is real, is that it might not be a single unified object, but rather a projection of multiple overlapping structures along the same line of sight. GRBs might be occurring in separate galaxy clusters that appear connected when viewed in two dimensions. However, even when correcting for this, the volume and scale of the clustering remain larger than expected. There are also implications for the age and shape of the universe. If such an immense structure formed within the universe's 13.8 billion-year lifespan, it would require either an unusually fast formation mechanism or a reevaluation of how structure formation proceeds on large scales.
It also raises questions about the curvature of the universe, whether it is truly flat as standard cosmology assumes, or whether subtle curvatures over vast distances could create misleading impressions of scale. This structure isn't the only one challenging cosmological models. Others, like the giant GRB ring, a proposed ring-shaped structure of GRBs about 5.6 billion light-years across, add to the mystery. These anomalies may eventually be explained within current models, or they may signal the need for new physics, just as the discovery of cosmic acceleration in the late 1990s led to the idea of dark energy.
For now, the Hercules Corona Borealis Great Wall remains one of the most puzzling structures in astronomy. It sits at the edge of our understanding, possibly a statistical artifact, possibly a signal of something profound.
More data, especially from next-generation GRB detectors and deep sky surveys, will be needed to resolve its nature. What is clear is that the universe continues to surprise. Each time astronomers believe they found the outer bounds of structure, something larger appears.
From stars to galaxies to clusters and superclusters, the universe forms patterns, and occasionally those patterns break the rules we thought were fixed. If the Hercules Corona Borealis, a Great Wall, is real, it forces a simple but unsettling realization. The universe may be less uniform and more complex than we've assumed for nearly a century. And in that complexity may lie the next revolution in our understanding of space, time, and the true shape of the cosmos. Stars are usually found in galaxies, gravitationally bound systems where size, gas, dust, and dark matter interact.
A galaxy can host billions or even trillions of stars, all orbiting a common center of mass. But not all stars stay in their galaxies forever. Some are violently ejected from their homes and launched into intergalactic space, destined to wander alone.
These are known as hypervelocity stars or intergalactic stars, and their very existence challenges the assumption that stars are permanently tied to galactic systems. The first hypervelocity star was discovered in 2005 by astronomers Warren Brown and colleagues at the Harvard-Smithsonian Center for Astrophysics.
It was a B-type star traveling at more than 850 kilometers per second, fast enough to escape the gravitational pull of the Milky Way. Since then, dozens more have been found. Many are traveling in trajectories that suggest they were ejected from the galactic center, shot outward like bullets from a gun. The main mechanism believed to eject these stars involves interactions with supermassive black holes.
If a binary star system, two stars orbiting one another, passes too close to the black hole at the center of a galaxy, intense gravitational forces can rip the system apart.
One star is captured into a tight orbit around the black hole, while the other is flung away at escape velocity. This is known as the Hill's mechanism, and it's thought to be the dominant source of hypervelocity stars in galaxies like the Milky Way.
Once ejected, these stars become interstellar and eventually intergalactic travelers. They move so fast that they escape the dark-mattered halo of their home galaxy and enter the vast voids of space between galaxies.
They're no longer bound to any system, orbiting nothing with no starry neighbors, just coasting through the vacuum at incredible speeds. The fastest known star of this kind is S5 HVS1.
Discovered in 2019, it's a hot, young, massive star traveling at about 1,700 kilometers per second, or roughly 6 billion kilometers per hour. Its velocity is so high that it is on track to escape the Milky Way entirely. Tracing its trajectory backward, astronomers believe it originated from the galactic center, where it was likely ejected by an encounter with the supermassive black hole Sagittarius A. This event happened about 5 million years ago, and now the star is heading into intergalactic space, never to return.
But not all rogue stars are high-speed bullets launched from galactic centers. Some are torn away during galactic mergers or close interactions between galaxies. When two galaxies pass near each other, tidal forces can stretch and distort their shapes, creating tails.
Long streams of stars and gas pulled away from the main galaxies. Some of these stars are flung so far that they end up outside any galactic boundary, left behind as the galaxies move on.
These stars aren't necessarily fast, but they are just as unbound. Lonely outliers drifting through the void. The Virgo cluster, a massive group of galaxies relatively close to the Milky Way, contains a significant population of such intergalactic stars.
Observation suggests that 10 to 20% of the total stellar mass in the cluster might reside outside of galaxies. These stars are detectable because they still shine mostly as red giants or evolved stars, and their collective light creates a faint glow known as intracluster light.
In some regions, this light has been used to map past galaxy collisions and merges, effectively reconstructing cosmic history through stellar debris. In 2014, astronomers using the Hubble Space Telescope detected a group of red giant stars between galaxies in the Abell 2744 cluster, a region nicknamed Pandora's cluster. These stars were clearly not part of any galaxy, and their distribution aligned with models of past galactic disruption. Their presence confirmed that galactic stripping, the process of stars being pulled out of galaxies, is not just theoretical, but a real and observable phenomenon.
The life of a rogue star is quiet but cold. Without the protection of a galaxy, these stars drift in near-perfect darkness. There is no ambient starlight, no interstellar medium to interact with, and no nearby gravitational anchors.
If the star is massive enough to go supernova, it will do so alone, its light briefly piercing a patch of space otherwise devoid of structure.
If it's a smaller star, like a red dwarf, it could burn for trillions of years, floating in isolation long after galaxies fade from view. From an observational perspective, these stars are extremely difficult to detect.
They are faint, fast-moving, and often far from any bright background that might provide contrast.
Most are only found when astronomers conduct large-scale astrometric surveys, like those done by the Gaia Space Telescope, which measures star positions and motions with high precision.
Gaia has provided data for over 1 billion stars and has already identified several hypervelocity candidates, giving astronomers insight into how stars are ejected and how common rogue stars might be. Rogue stars may also carry planetary systems.
If a star with orbiting planets is ejected from a galaxy, its planets may remain gravitationally bound and follow it into intergalactic space. In such a scenario, the planets would orbit their star as normal, but with no surrounding galaxy, no visible night sky full of stars, just a cold, empty universe.
These systems would be nearly impossible to detect, but in theory, they could exist. Another possible source of intergalactic stars is supernova kicks. When a massive star explodes, the resulting neutron star or black hole can receive a stronger symmetric push or pick, sending it off at high speed.
If this happens near the edge of a galaxy, the remnant can escape into intergalactic space. This is one way that isolated neutron stars and black holes may end up drifting alone in the void.
The study of these stars is more than just a curiosity. Understanding how and why stars are ejected helps astronomers learn about the dynamics of galactic cores, the behavior of supermassive black holes, and the history of galaxy collisions.
It also helps refine models of dark matter halos, since the escape velocity of a star depends on the total mass of the galaxy, including its unseen components.
As detection methods improve, astronomers expect to find many more rogue stars, not just in the Milky Way, but in other galaxies and clusters. Some may travel for billions of years before reaching intergalactic space.
Others may already be deep in the cosmic void, unnoticed and unbound. These stars challenge the idea that galaxies are closed systems. They show that gravity does not always win and that the universe, even at the scale of stars, is dynamic, chaotic, and full of exceptions.
In the vastness of space, some stars don't follow the crowd. They go their own way, fast, far, and alone. Imagine an object so bright that it outshines the combined light of hundreds of billions of stars. An object that can be detected billions of light years away, providing a beacon from the early universe. These are quasars, some of the most luminous and energetic objects known to science.
Though they look like stars in telescopes, quasars are in fact the intensely active centers of distant galaxies powered by supermassive black holes consuming matter at extraordinary rates. The term quasar is short for quasi-stellar radio source, a name coined in the 1960s when these objects were first discovered through their intense radio emissions. At first, astronomers were puzzled by their properties. They appeared point-like, like stars, but had unusual spectral lines that indicated they were incredibly distant and luminous.
The puzzle was solved when it was understood that quasars are the active nuclei of galaxies with black holes, millions to billions of times the mass of the Sun at their cores.
At the heart of a quasar lies a supermassive black hole surrounded by an accretion disk, a swirling, flattened ring of gas and dust falling inward.
As matter spirals closer to the event horizon, it heats up to millions of degrees due to gravitational and frictional forces, emitting vast amounts of electromagnetic radiation across the spectrum, from radio waves to X-rays.
This emission can be thousands of times more luminous than the entire galaxy that hosts the black hole. Quasars are powered by accretion, the process of matter falling into the black hole's gravitational well.
Unlike stars that generate energy through nuclear fusion, quasars release energy by converting the gravitational potential energy of infalling matter into radiation. This process is remarkably efficient. Up to 10% or more of the mass energy of the accreted material is converted into light, far exceeding the efficiency of nuclear fusion and stars.
Some quasars have luminosities exceeding 10 to the 14 times the Sun's luminosity. For perspective, the Milky Way's total stellar luminosity is about 10 to the 10 solar luminosities. That means a quasar can be 10,000 times brighter than our entire galaxy.
This intense brightness allows quasars to be observed across much of the observable universe, serving as cosmic lighthouses that help astronomers study the early cosmos. Quasars also display remarkable variability.
Their brightness can fluctuate on timescales of days to years, indicating that the emitting region is very compact, no larger than our solar system.
This variability, combined with their spectral signatures, confirms the central role of accretion disks and black holes in producing their energy. One of the most famous quasars is 3C273, located in the constellation Virgo, about 2.4 billion light-years away.
It was the first quasar ever to be identified optically and remains one of the brightest. Its discovery was a turning point in astronomy, leading to the realization that supermassive black holes and active galactic nuclei, AGN, are common in the universe.
Quasars are not static phenomena. They represent an active phase in a galaxy's life cycle. Over time, as the black hole consumes available gas and dust, the accretion rate drops, and the quasars dims.
The galaxy then transitions into a more quiescent state with a relatively inactive nucleus. Some galaxies, like our own Milky Way, may host dormant supermassive black holes that could become quasars again if they accrete enough matter.
The study of quasars has profound implications for understanding galaxy formation and evolution. The growth of supermassive black holes and their feedback from their energy output can regulate star formation in their host galaxies.
Powerful quasar winds and jets can blow gas out of galaxies, quenching star formation and shaping galactic environments over millions of years. Quasars also serve as cosmological probes.
Because their light travels for billions of years, it carries information about the conditions of the early universe. Spectroscopic analysis of quasar light reveals the composition, temperature, and motion of intergalactic gas clouds it passes through, allowing astronomers to study the large-scale structure of the universe and the evolution of elements over cosmic time.
While many quasars emit strong radio waves, some are radio quiet, and others produce jets of relativistic particles that extend well beyond their host galaxies. These jets can influence the intergalactic medium and are often detected in radio and X-ray observations. Understanding these jets is key to understanding how black holes impact their cosmic neighborhoods. Recent observations with advanced telescopes like the Hubble Space Telescope, Chandra X-ray Observatory, and the Atacama Large Millimeter Submillimeter Array, ALMA, have revealed detailed structures in quasar host galaxies, including star formation triggered or suppressed by quasar activity.
They also uncovered dust lanes, molecular gas flows, and complex interactions between the black hole and its surroundings. The earliest quasars detected at redshifts greater than 7 formed less than 1 billion years after the Big Bang.
Their existence challenges models of black hole growth, suggesting that supermassive black holes can form very rapidly in the early universe. Understanding how these massive black holes grow so quickly remains an active area of research.
In summary, quasars are cosmic powerhouses, the luminous beacons of the universe's most energetic phenomena,
powered by gravity's darkest corners. They illuminate the cosmos, reveal the nature of galaxies, and test the laws of physics under extreme conditions.
Studying quasars helps us understand not only how black holes work, but how galaxies grow, evolve, and interact on the grandest scales. Imagine looking at the cosmos and realizing that galaxies, including our own Milky Way, aren't just drifting randomly through space.
Instead, they're all moving toward a mysterious region, a cosmic heavyweight whose gravitational pull tugs at galaxies across hundreds of millions of light years. This phenomenon is known as the Great Attractor, a vast, hidden gravitational anomaly that challenges our understanding of the large-scale structure of the universe.
The story of the Great Attractor begins in the 1970s and 1980s, when astronomers noticed something strange about the motions of galaxies. By measuring redshift, the stretching of light to longer wavelengths caused by cosmic expansion, they expected galaxies to recede from us uniformly.
But some galaxies showed peculiar velocities moving toward a specific region in the sky, beyond what cosmic expansion could explain. This unexpected motion suggested the presence of a massive gravitational source pulling matter towards it.
The region exerting this force is centered near the constellations Norma and Triangulum Austral, 150 to 250 million light-years away. The mass responsible for the Great Attractor is immense.
Estimates suggest it contains mass equivalent to thousands of galaxies, enough to influence the motion of galaxy clusters over a vast volume. Despite its massive influence, the Great Attractor is difficult to observe directly.
The reason is the zone of avoidance, a part of the sky obscured by the dense plane of our own Milky Way galaxy. Dust, gas, and stars in the Milky Way block much of the light from distant galaxies lying in that direction, creating a sort of cosmic shadow.
This makes it challenging to pinpoint exactly what constitutes the Great Attractor. To peer through this obscured region, astronomers have relied on X-ray observations in surveys using radio waves and infrared light, which can penetrate the dust more effectively than visible light.
These observations reveal a complex region filled with galaxy clusters, superclusters, and massive structures, including the Norma cluster, AEL 3627, one of the most massive galaxy clusters nearby and a major component of the Great Attractor.
The Great Attractor is not a single object, but a gravitational focal point formed by the combined mass of numerous galaxy clusters, dark matter, and gas. It acts like a cosmic drain, pulling nearby galaxies and clusters towards its center.
Our own local group, which includes the Milky Way and Andromeda galaxies, is part of this large-scale flow, moving at hundreds of kilometers per second towards this gravitational hub. However, the Great Attractor itself is part of an even larger structure.
Further studies have revealed that it lies within the Laniakea supercluster, an enormous network of galaxies spanning over 520 million light-years. Laniakea encompasses the Milky Way and several other galaxy groups, all gravitationally bounded and moving toward a common center near the Great Attractor.
This supercluster redefines our cosmic neighborhood and highlights how gravity shapes the universe on colossal scales. The Great Attractor's discovery reshaped cosmology by showing that the universe's structure is hierarchical and anisotropic. Matter isn't evenly distributed, but clumps together in webs, filaments, walls, and voids. It also revealed that the universe is dynamic, with galaxies flowing along gravitational pathways rather than remaining static. Yet many questions remain. The exact nature of the mass concentration responsible for the Great Attractor is still not fully understood.
Dark matter, which makes up most of the universe's mass, plays a critical role, but is invisible to telescopes. The visible galaxy clusters account for only part of the gravitational pull, suggesting a large amount of unseen matter is concentrated in this region. Furthermore, more recent observations have uncovered what's called the Shapley supercluster, an even larger mass concentration located about 650 million light-years away. Some scientists suggest that the Great Attractor is only a local gravitational dip within a more extensive flow toward the Shapley supercluster.
This hints at a cosmic landscape of overlapping gravitational influences that guide the motion of galaxies over billions of light years. Understanding the Great Attractor is crucial for measuring the velocity field of galaxies and refining models of cosmic expansion. It also helps calibrate the distance ladder, the set of methods astronomers use to measure distances in the universe by accounting for peculiar velocities caused by gravitational pulls, which can distort redshift-based distance estimates. In practical terms, the Great Attractor influences the cosmic microwave background CMBB through effects like the kinematic Sun-Zeldich effect, where galaxy clusters moving through the CMB imprint subtle temperature fluctuations. These observations provide independent evidence of large-scale motions consistent with the Great Attractor's pull. The search to map the Great Attractor continues with new instruments, including the Arosita X-ray telescope and surveys like the Dark Energy Survey, DEES, which aim to better resolve the hidden structures behind a zone of avoidance.
As we peel back layers of dust and gas obscuring our view, we expect to uncover more about the composition and extent of this gravitational giant. Ultimately, the Great Attractor is a cosmic reminder that galaxies are not isolated islands adrift in space. Instead, they are part of a vast cosmic dance choreographed by gravity on unimaginable scales. The invisible hand of the Great Attractor guides this dance, pulling galaxies together, shaping the architecture of the universe, and reminding us of the hidden forces at work in the cosmos. In July 2007, astronomers analyzing old data from the Parkes Radio Telescope in Australia discovered something unexpected. A powerful millisecond-long burst of radio energy that had originated from deep space. It was extremely bright, incredibly brief, and came from well beyond the Milky Way.
That first detection was later called the LoRa burst, and it marked the beginning of one of the most puzzling modern mysteries in astrophysics, the discovery of fast radio bursts, or FRBs. At first, these signals seemed to be one-time events.
FRBs appeared randomly in the sky and then disappeared, often without warning or any repeated signal. They came from all over the sky and had no obvious pattern. That alone was strange enough. Radio pulses from outside our galaxy, lasting just a few milliseconds, yet powerful enough to release as much energy in that instant as the sun does in a day. For years, astronomers wondered whether these bursts were caused by neutron stars, black holes, colliding objects, or even some unknown kind of astrophysical explosion. Then something changed. In 2016, astronomers using the Arecibo Observatory detected a signal known as FRB 1211102.
And this one repeated. It was a breakthrough. Unlike other ERBs which were seen only once and then never again, FRB 12112 kept coming back. Dozens of bursts were detected from the same point in the sky.
This proved definitively that at least some ERBs are not cataclysmic one-time events. Whatever was producing these pulses wasn't being destroyed in the process. It was something persistent, repeating, and stable.
The source of FRB 12112 was eventually traced to a dwarf galaxy more than 3 billion light-years away. This galaxy was small, low in heavy elements, and had signs of ongoing star formation. The precision localization achieved using interferometry with telescopes like the Very Large Array, VLA, allowed scientists to rule out many Earth-based or local sources of interference. This was not noise or a glitch. It was genuine extragalactic radio emitter of unknown origin.
Since then, many more repeatings have been found. Some, like FRB 1809 Monstist JO month date plus 65, display regular patterns. In this case, the bursts followed a 16-day cycle active for 4 days, then silent for 12, and then repeating.
This rhythmic behavior hinted at a celestial engine with a clock-like mechanism, possibly a rotating neutron star, a binary system, or something even stranger. Theories for repeating FRBs vary. One idea is that they're caused that magnetars, highly magnetized neutron stars.
Magnetos can produce sudden outbursts of energy when their magnetic fields rearrange or their crusts crack under pressure. In 2020, the Magneta SGR 1935 plus 214, located within our own Milky Way, emitted a short radio burst with FRB-like characteristics, lending credibility to this theory.
However, the burst was far less energetic than the extragalactic FRBs, suggesting either a different mechanism or that only the brightest magnetoflares are detectable at long distances.
Other ideas include interactions between neutron stars and black holes, collisions of compact objects, or even exotic physics such as cosmic strings or dark matter interactions. More speculative ideas suggest technological sources, advanced civilizations using radio bursts as beacons or propulsion systems. While there is no evidence supporting the artificial origin theory, the regularity and intensity of some RFRBs make them stand out from other natural signals. What makes FRB 121102 especially intriguing is its dispersion.
As the radio waves travel through space, lower frequency components are delayed more than higher frequency ones, a signature of traveling through ionized plasma. This delay gives astronomers a way to estimate how much matter the signal passed through, effectively making cosmic probes of the intergalactic medium. The more dispersed the signal, the farther it likely traveled, and the more it tells us about the invisible matter between galaxies. Some FRBs, like 12101 Non-2, come with additional clues. The bursts are highly polarized, meaning the radio waves are aligned in a particular direction. This suggests the signal passed through a strong magnetic field, possibly near a black hole or inside a supernova remnant. In fact, FRB 121 Norman 2 appears to be located in a star-forming region within its host galaxy, perhaps close to a young supermassive black hole or a dense cluster of neutron stars.
As of now, astronomers have cataloged hundreds of FRBs, with dozens confirmed to repeat. However, not all repeaters behave the same. Some emit frequent bursts, sometimes minutes apart. Others go quiet for weeks or months. Some are bright, some are faint, some are localized precisely.
Others are still poorly understood. The diversity suggests that FRBs may not come from a single type of object or event, but rather represent multiple astrophysical processes.
One of the most surprising discoveries came in 2020 when astronomers found a repeating FRB from within our galaxy. It was the first time an FRB had been detected so close to home, and it confirmed that at least magnetars can produce FRB-like signals.
This connection bridged the gap between exotic deep space bursts and known stellar remnants. Still, many questions remain. Why do only some magnetars emit FRBs? What explains the periodicity of certain repeating bursts? Why are some signals extremely bright and others faint? And perhaps most intriguingly, are we only seeing the tip of the iceberg, with the vast majority of FRBs going undetected due to instrument sensitivity, direction, or obscuration? New telescopes are helping to answer these questions. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has discovered hundreds of FRBs, revolutionizing the field by monitoring large swaths of the sky continuously. The upcoming Square Kilometer Array, SKA, is expected to detect thousands more and provide precise localizations.
These instruments will help astronomers map the full FRB population, measure their distribution, and ideally, determine their exact origins. The implications of understanding are broad.
Beyond their own mystery, they serve as tools for probing the structure of the universe, mapping cosmic magnetism, and studying matter that's otherwise invisible. Their dispersion measures can even help refine estimates of the cosmic baryon content, resolving discrepancies in how much normal matter we think exists versus how much we observe.
The fact that some FRBs repeat makes them especially valuable. Unlike supernova or gamma-ray bursts, which happen once and are gone, repeaters offer multiple opportunities to observe, study, and test theories.
With each burst, they give astronomers a new puzzle piece, another signal from the depths of time and space, whispering a message that science is still struggling to decode. In summary, repeating FRBs are one of the most puzzling modern phenomena in astrophysics. They are brief, intense, and in some cases rhythmic. We know they're real. We know they come from far beyond our galaxy, and we know they carry valuable data about the cosmos, but we still don't fully know what they are.
And until we do, each repeating burst is a reminder. The universe is full of signals, and we've just started listening. Among the deadliest and most extreme objects in the universe are magnetars, ultra-dense, hypermagnetized stellar remnants that defy comprehension.
These are a subclass of neutron stars, already some of the densest forms of matter outside black holes. But what sets magnetars apart is their mind-bending magnetic fields, the strongest known in the cosmos. Fields so intense they could theoretically strip electrons from atoms even from a distance of hundreds of thousands of kilometers. And yes, are powerful enough to wipe a credit card's magnetic strip from halfway across the galaxy. Let's start with the basics. When a massive star, typically 10 to 25 times the mass of the Sun, explodes in a supernova, its core collapses into a neutron star, a dense object with about 1.4 times the Sun's mass, crammed into a sphere just 20 kilometers wide. The result is an object so dense that a single teaspoon of neutron star matter would weigh 1 billion tons. But a few of these neutron stars are born spinning rapidly and with unusually strong magnetic fields. These are the magnetars. A typical neutron star has a magnetic field on the order of 10 to 12 GeV. For comparison, Earth's field is about 0.5 GeV. But magnetars crank that number up to an absurd 10 to 15 GeV. 1,000 times stronger than a regular neutron star and 1 trillion times stronger than Earth's magnetic field. For scale, the most powerful magnets humans have built, like those in MRI machines or particle accelerators, barely reach 100,000 Gauss.
At this intensity, the magnetic field alters the structure of atoms, flattening electron clouds and turning spherical atoms into elongated, cigar-shaped particles. The quantum vacuum around the magnetar doesn't behave normally either.
Space itself becomes Borg-ring, meaning light waves passing through are split and polarized by the magnetic field, an effect called vacuum biorigins, which has actually been observed around magnetars using optical telescopes.
So yes, that joke about magnetars erasing credit cards, it's rooted in real physics. A magnetic field that strong would induce electric currents in nearby objects, distort chemical bonds, and destroy electronics without ever touching them.
If you somehow brought a credit card within a few hundred kilometers of a magnetotar, its magnetic strip would be completely scrambled. If you brought yourself closer, well, your molecular structure would start to come apart long before you arrived.
But magnetars don't just sit there quietly with their terrifying magnetic fields. They're prone to outbursts. As the intense magnetic field shifts and rearranges, it can crack the neutron star's crust, releasing huge amounts of energy in the form of gamma rays, X-rays, and radio waves.
These are called starquakes, the cosmic equivalent of tectonic plates shifting on Earth, only made of super-dense nuclear matter. In 2004, a magnetar in our galaxy, SG 180620, located about 50,000 light-years away, released the most powerful flare of gamma rays ever recorded.
The burst lasted just 2 seconds, but in that flash it released more energy than the sun emits in 250,000 years. For a brief moment, it actually saturated satellite detectors and caused Earth's upper atmosphere to ionize despite being halfway across the galaxy.
Had it been only a few light-years away, it might have wiped out Earth's ozone layer or worse. These flares make magnetars candidates for some fast radio bursts, those mysterious millisecond-long cosmic radio signals that repeat.
In 2020, astronomers detected an FRB-like burst from the magnetar SG 1935 plus 2154, located within the Milky Way. It wasn't as powerful as extragalactic FRBs, but it provided the first direct evidence that magnetars can produce FRB-like emissions.
This made them one of the leading explanations for the mysterious signals we've discussed previously. Magnetars are also linked to soft gamma repeaters and anomalous X-ray pulses, two types of strange objects that emit irregular high-energy bursts.
Initially, these were thought to be different categories of exotic stars, but we now understand they're likely just different observational behaviors of magnetars. How many magnetars exist? We've discovered only about 30 confirmed magnetars in our galaxy, but suggested models there may be thousands.
They're rare and short-lived in cosmic terms. The intense magnetic fields that define them decay over time, usually within 10,000 to 100,000 years, which is why we don't see them often.
Once the field weakens, the magnetar may settle into life as a more typical neutron star or radio pulsar. So, how do they form? Magnetars are born in supernova explosions, just like regular neutron stars, but under highly specific conditions. If the progenitor star has the right mass, composition, and rotational speed, the collapsing core can amplify magnetic fields through dynamo effects during the explosion. The magnetic field strengthens rapidly and gets locked in as the neutron star forms.
Interestingly, the birth of a magnetar might also explain some superluminous supernova explosions that are 10 to 100 times brighter than typical supernova. In these cases, it's believed the newly formed magnetar injects additional energy into the expanding debris, lighting it up far beyond what radioactive decay alone could achieve.
This is an area of active research.
linking magnetophysics with some of the brightest events in the universe. Some magnetars may also form from neutron star mergers, the same kinds of collisions that produce gravitational waves and collisions.
In some scenarios, the merger doesn't immediately create a black hole, but instead forms a hypermassive magnetar, one that survives for a few milliseconds to seconds before collapsing under its own weight. During that brief window, it can release incredible amounts of energy.
The study of magnetars has pushed the limits of both observational astronomy and theoretical physics. These objects are natural laboratories for testing physics under conditions that can't be reproduced on Earth, including high-density nuclear matter, ultra-strong magnetic fields, and quantum effects in curved spacetime. And yet, for all their violence, magnetos are invisible to the naked eye. If you looked at the sky where SG 18062 resides, you wouldn't see anything unusual.
But buried in that point of light is an object so extreme, so concentrated, and so volatile that its mere existence reshapes our understanding of what stars can become. In short, magnetos are like cosmic wrecking balls, small, dense, and dangerously magnetic.
They may not be common, but their influence, both physical and theoretical, extends across astrophysics. They represent the upper limits of how intense a magnetic field can be, how compact matter can become, and how violent the universe can get without collapsing into a black hole.
In space, collisions are not rare. But when most people imagine galaxies colliding, they picture a violent, catastrophic crash. Stars smashing into stars, planets torn from their orbits, and entire systems disintegrating. The truth is stranger.
Galaxies do collide, often spectacularly, but in many cases, they pass through one another like ghosts, continuing on their paths almost unaffected, at least in terms of direct impacts. It's one of the most counterintuitive realities in astrophysics. Galaxies collide without their stars actually hitting.
The reason lies in the sheer scale of galaxies. While galaxies can contain hundreds of billions of stars, those stars are separated by enormous distances. In the Milky Way, the average distance between stars is about 5 light-years.
So when two galaxies merge, the odds of any two stars colliding directly is incredibly low, like throwing two clouds of sand at each other from across a football field and expecting grains to hit. What does collide, however, is gravity and gas.
A famous example of a galactic collision is the pair known as the Antennae galaxies, located about 45 million light-years away in the constellation Corvus. These two spiral galaxies are currently merging.
And as they pass through each other, tidal forces distort their shapes, flinging out long streams of stars and gas into space. These tidal tails, shaped like antennae, are visible evidence of the gravitational interactions reshaping both galaxies. While the stars mostly avoid direct contact, the gas and dust within galaxies does not. When interstellar gas clouds collide, they compress, heat up, and collapse, often triggering massive bursts of star formation.
These are called starburst events, and they light up galactic mergers with new stars forming at rates much higher than normal. In the antenna galaxies, the collision has sparked the formation of thousands of new star clusters.
Over time, typically hundreds of millions to billions of years, the gravitational dance between colliding galaxies causes their orbits to decay. They spiral inward and eventually merge into a single, larger galaxy.
In most cases, the end result is not a bigger spiral galaxy, but an elliptical galaxy, rounder, more chaotic, and with less defined structure. The beautiful arms and disks of the original spirals are disrupted and rearranged by gravitational forces into a more uniform shape.
Our own Milky Way galaxy is on a collision course with its nearest large neighbor, the Andromeda Galaxy M31. The two are set to collide in about 4.5 billion years.
And simulations suggest that they will pass through each other several times before finally settling into a merged elliptical galaxy, sometimes nicknamed Milcom-Dicka. Again, most stars, including possibly our Sun, will survive the process.
The solar system may be flung to a different location in the new galaxy, but it's unlikely to be destroyed by direct collision. Galactic collisions also drive the growth of supermassive black holes at the centers of galaxies.
When galaxies merge, the central black holes are pulled toward each other by gravity, eventually forming a binary black hole system. These black holes orbit each other, lose energy through gravitational waves, and ultimately merge in a violent event that may be detectable by future observatories like the Laser Interferometer Space Antenna, LISA.
The merged black hole ends up more massive and more active, sometimes powering a quasar. Observations from the Hubble Space Telescope and ground-based observatories have captured stunning images of galactic collisions in progress. In some, like NGC 4038 and NGC 4039, the antennae, the shapes are clearly distorted by gravitational tides. Others, like NGC 4676, nicknamed the mice galaxies, show long tails of stars stretching out as the galaxies swing past each other.
These interactions help astronomers understand how galaxies grow and evolve. Galactic collisions are not just common, they're essential to how galaxies form. The hierarchical model of structure formation suggests that galaxies in the early universe began and grew small and larger through a series of mergers.
Many galaxies we see today are the result of multiple past collisions, their shapes and contents shaped by ancient encounters. Elliptical galaxies, in particular, often show signs of past mergers, distorted halos, shells, and star streams that are relics of long-dead companions.
Another well-known case is the Bullet Cluster, a pair of galaxy clusters that pass through each other. In this case, the galaxies themselves and their stars mostly passed through, but the hot gas clouds collided and slowed down, separating from the stars. This separation of mass and gas provided one of the strongest pieces of observational evidence for dark matter. The stars and galaxies which were not slowed marked the locations of the total mass, which didn't align with the X-ray detected gas. The extra mass inferred from gravitational lensing was attributed to dark matter. While collisions between galaxies may look serene from a distance, they can be disruptive for planetary systems. As galaxies interact, their gravitational fields fluctuate, possibly perturbing star systems, stirring up gas clouds, and altering stellar orbits. These changes can trigger new star formation, but they can also cause instabilities in existing systems.
If a star passes too close to another during a galactic pass, it might disturb planets or send objects like comets into new orbits. But these effects are still rare and spread across immense distances.
Another surprising feature is that galaxies can collide and remain visibly separate for billions of years. The process isn't instantaneous, it's a slow gravitational wave. As they pass through one another, galaxies can be stretched, spun, and twisted.
But they can also continue on their paths and collide again later. This happens because of dynamical friction, a process where gravitational interactions with surrounding matter slow down massive objects. Over time, this causes the galaxies to settle into one combined system.
Mergers can also trigger active galactic nuclei, AGN. As the gas in colliding galaxies falls towards the central black holes, it heats up and emits radiation. In some cases, this results in quasars or blazars, some of the brightest objects in the universe.
So, while the stars pass through each other, the interaction of gas and gravity can light up the universe in dramatic ways. One final detail: not all collisions are between equals. Some involve large galaxies devouring smaller ones.
These are called minor mergers, and they happen frequently. The Milky Way is currently in the process of absorbing several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which has already been torn apart and wrapped around the Milky Way in long streams.
These minor mergers are thought to build up galactic halos, enrich them with stars, and contribute to the complex structure we observe in galaxies today. In summary, galaxies do collide, and they often pass through each other without direct stellar crashes.
The collisions are slow, gravitational, and transformative. They reshape galaxies, trigger starbursts, feed black holes, and build the large-scale structure of the universe. They also remind us that space, while vast and mostly empty, is not static. Even the largest structures are in motion.
And over cosmic time, nothing stands still. According to modern cosmology, the universe is approximately 13.8 billion years old, a figure derived from measurements of the cosmic microwave background radiation, expansion rate, Hubble constant, and Big Bang nucleosynthesis.
So when astronomers find a star that appears to be older than that, something is clearly off. And that's exactly what happened with a star called HD 183, nicknamed the Methuselah star.
A star whose estimated age once appeared to be older than the universe itself. HD 140283 is located about 190 light-years away in the constellation Libra. It's a subgiant star, meaning it's in a transitional phase between a main sequence star and a red giant.
What makes it special is its extremely low metallicity. That is, it contains very few elements heavier than helium. In astrophysics, metals include all elements heavier than helium.
And stars with extremely low metallicity are considered population 2 stars, formed very early in the universe when only hydrogen, helium, and trace amounts of lithium were abundant.
The Methuselah star has less than 250th the iron content of the Sun, suggesting it formed from gas that hadn't been significantly enriched by earlier generations of stars. This alone hints at extreme age.
But the surprise came when astronomers tried to determine just how old it actually was. Using data from parallax measurements, spectroscopy, and stellar evolution models, astronomers in the early 2000s estimated HD 132 Freese's age to be around 14.46 billion years, with an uncertainty of plus 0.8 billion years.
Even at the lower end of that range, it still pushed the limits of the universe's accepted age. At the higher end, it seemed to predate the Big Bang. This was not just a minor discrepancy, it was a major headache for cosmologists.
If the universe is 13.8 billion years old, nothing in it should be older than that. So how could this single star appear to defy that fundamental boundary?
The answer lies not in rewriting the age of the universe, but in re-evaluating the methods used to age-date stars. Estimating stellar ages is not straightforward.
It involves complex models of stellar interiors, nuclear fusion rates, opacity, mass loss, and chemical composition, all of which introduce uncertainty.
For a star like HD Wanton's 283, even a small error in any one of these parameters can result in age estimates that are off by hundreds of millions of years.
One key variable is distance. Parallax measurements determine how far away a star is, which in turn helps determine its intrinsic brightness, a key input for age models. Early parallax data had large uncertainties. When the Hubble Space Telescope was used to obtain a more precise parallax measurement in 2013, the estimated age of HD 1402283 was revised to 13.7 billion years, with an uncertainty of plus 0.7 minus 0.17 billion years.
This brought the star's age just within the bounds of the universe's age, resolving the immediate conflict, at least statistically. Even with the updated age, HD 402283 remains one of the oldest known stars in the universe.
It likely formed just a few 100 million years after the Big Bang, possibly from the remnants of the very first stars, the hypothetical population 3 stars, which were massive, short-lived, and left behind only trace elements.
HD 132 US or 3 carries the chemical fingerprint of an early universe that hadn't yet been enriched by multiple cycles of star formation and supernova explosions.
The Methuselah star is important because it serves as a time capsule, preserving conditions from the early universe in its composition and structure. Its very existence helps constrain models of galaxy formation, chemical evolution, and stellar nucleosynthesis.
It tells astronomers when certain types of stars could first form, how long it takes to reach different phases of stellar life, and how fast elements like iron and carbon build up in galaxies. It's also a reminder of the limits of measurement.
The older than the universe result wasn't a sign that the Big Bang theory was wrong. It was a reflection of how difficult it is to pin down age with absolute certainty. Astronomical data always comes with error bars.
And occasionally, those bars overlap in ways that produce surprising or seemingly paradoxical results. When measurements become more precise, those paradoxes often resolve themselves. But HD Z-Thorn 283 isn't alone in stretching cosmic timelines.
Other extremely metal-poor stars have been found with estimated ages approaching or slightly exceeding the universe's age, depending on the model used. These include stars like BD plus 17 D3248 and HE 1523, both of which have extremely low metallicity and old age estimates.
These cases highlight how stellar archaeology complements cosmology. While observations of the cosmic microwave background and the large-scale structure of the universe provide one way to measure the universe's age, ancient stars offer a completely different method.
If their ages consistently exceeded 13.8 billion years, it might suggest the fundamental problem with cosmological assumptions, but so far most results are converging barely around the same timeline.
Another wrinkle is that the Hubble constant, the rate at which the universe is expanding, is itself the subject of debate. Measurements using the cosmic microwave background from the Planck satellite give one value.
Direct measurements using supernova and Cepheid variables give another slightly higher one. A higher Hubble constant would imply a younger universe, potentially reviving the conflict with the Methuselah star. This is known as the Hubble tension, and it remains one of the most active and unresolved questions in modern cosmology. So while HD 1283 may no longer technically predate the universe, it still occupies an extreme edge case, old enough to probe the earliest era of stellar formation,
but close enough to the boundary of known physics to keep astronomers on the edge. It forces improvements in stellar models, challenges cosmologists to refine the age of the universe, and serves as a constant reminder that our cosmic timelines are still open to revision.
In summary, HD 143 Intanu 283, the Methuselah star, doesn't actually break the laws of physics, but it came close enough to spark a serious re-examination of how we date stars and how we define the universe's history.
It's a stellar anomaly that helped tighten science, refine models, and prove once again that even a single object shining quietly in the sky can push the boundaries of what we think we know.
In the large-scale map of the universe, galaxies don't appear randomly scattered. Instead, they form a vast, intricate web of structure, an interconnected network of filaments, clusters, walls, and voids.
Among these structures, one of the largest ever discovered is simply known as the Great Wall, but even that name doesn't capture the full scale of what we're dealing with.
A cosmic structure that stretches across 1.4 billion light-years, made of galaxies bound together by gravity into a massive spine-like ridge of matter. The discovery of the Great Wall began in the 1980s and 1990s as astronomers undertook massive redshift surveys to map the positions and distances of galaxies across the sky. In 1989, Margaret Geller and John Hushra of the Harvard-Smithsonian Center for Astrophysics revealed a striking finding from the CFA2 redshift survey: an extended region of space densely packed with galaxies forming a sheet-like arrangement.
This became known as the CFA2 Great Wall, or simply the Great Wall, the largest known structure at the time. Its length, about 500 million light-years, stunned researchers. But it was just the beginning.
Over the next decades, larger and deeper surveys revealed even more massive structures. One of these, found in 2003, was the Sloan Great Wall, a filament discovered in data from the Sloan Digital Sky Survey, SDSS. The Sloan Great Wall turned out to be roughly 1.37 billion light-years long, making it nearly 3 times the size of the original CFA2 Great Wall. It remains one of the largest coherent structures ever detected in the observable universe.
To understand what makes the Great Wall so remarkable, it helps to look at what it's made of. It's not a solid object. It's a galaxy filament, a thread-like formation composed of clusters and superclusters of galaxies arranged in a relatively narrow band, but stretching over an immense distance.
Each cluster contains hundreds or thousands of galaxies. The entire structure includes millions of galaxies, all gravitationally connected and embedded in a web of dark matter and intergalactic gas. The scale is hard to grasp.
Light takes 1.4 billion years to cross the length of the Sloan Great Wall. That's about 10% of the age of the universe itself. If you could somehow observe the structure from outside, from a hypothetical point billions of light-years away, the Great Wall would look like a cosmic scar etched across a huge region of space.
This raises a fundamental question. How do such large structures form? According to current models of cosmology, structure in the universe forms through a process called gravitational instability.
Tiny fluctuations in the density of matter seeded in the very early universe grew over billions of years as gravity pulled matter into denser regions.
Over time, this gave rise to the cosmic web, a sponge-like network of dense filaments where galaxies form, separated by vast empty voids. Simulations like the Millennium Simulation and more recent ones from the Illustris and Eagle projects reproduce structures similar in shape and scale to the Great Wall.
Although the very largest walls, like Sloan's, push the limits of what we'd expect,
Some scientists have debated whether a structure this large violates the cosmological principle, the idea that the universe is homogeneous and isotropic, the same everywhere on large scales.
But most evidence suggests that such structures can still emerge naturally in a universe governed by cold dark matter and dark energy. Still, the Great Wall blurs the line between structure and anomaly.
It is so massive, so extended, and so coherent that it challenges simple statistical explanations. Some astronomers even question whether it's truly a single object, or rather a chance alignment of several superclusters along the same line of sight.
The difference matters because if these kinds of walls are too frequent or too large, they could contradict our best cosmological models. Other superstructures rival the Great Wall in size, and some even exceed it, depending on how structure is defined.
For example, the Hercules Corona Borealis Great Wall, discovered in 2013, has an estimated length of 10 billion light-years, making it the largest known structure in the universe by a wide margin.
However, the evidence for this wall is based on the clustering of gamma-ray bursts, and it remains a controversial finding. Many cosmologists remain skeptical, as such a massive structure would challenge the assumption that the universe becomes statistically uniform beyond certain scales.
Unlike a building wall, the Great Wall isn't static or unchanging. Galaxies within the structure are moving, evolving, merging, and forming stars. The wall itself will change over time.
Gravity will continue to shape it, pulling some clusters closer and possibly causing portions to collapse into even denser regions. Over tens of billions of years, dark energy will accelerate the universe's expansion and begin to tear these massive structures apart by stretching space itself.
Despite its scale, the Great Wall is not visible to the naked eye from Earth. No single telescope can photograph it in full, as its span covers too much of the sky and lies too far away.
It was only discovered by measuring the redshifts of hundreds of thousands of galaxies, converting their positions into a three-dimensional map. The wall revealed itself as a pattern in data, not in light.
Its discovery is a reminder of how much we owe to survey science. The painstaking work of cataloging objects across large parts of the sky.
Tools like the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and now the Dark Energy Spectroscopic Instrument, DESI, continue to uncover ever more detailed maps of the universe, revealing that space is anything but empty and uniform. The existence of these giant walls also affects how we understand cosmic flows, the motion of galaxies under the influence of gravity. Regions near large structures, like the Sloan Great Wall, can have bulk flows where hundreds of galaxies move together toward a dense region.
These flows help test models of gravity, dark energy, and cosmic inflation, giving us tools to refine our understanding of how the universe behaves on the larger scales. In some sense, the Great Wall and its like represent the edge of our comprehension.
They don't break physical laws, but they remind us that the universe is structured, dynamic, and vastly more intricate than early cosmology imagined. The universe isn't just expanding.
It's sculpting itself over eons into a web of matter and voids, with galaxy filaments as the skeleton. In summary, the Sloan Great Wall is one of the largest known structures in the universe.
A 1.4 billion light-year filament of galaxies and clusters forming a kind of cosmic architecture. It's too vast to see, too massive to ignore, and just strange enough to keep scientists asking whether we fully understand what the universe is made of and how it all fits together. When we look out into the night sky, we're not just seeing stars. We're looking back in time. Because light travels at a finite speed, about 299,792 kilometers per second, distant galaxies appear not as they are now, but as they were when the light we're seeing left them. The farther away an object is, the older the light we receive. This simple truth leads us to one of the most profound boundaries in modern science, the edge of the observable universe.
The observable universe is the part of the cosmos from which light or any signal has had time to reach us since the Big Bang, 13.8 billion years ago.
But due to the expansion of space itself, that boundary is much farther than 13.8 billion light-years. In fact, the radius of the observable universe is about 46.5 billion light-years, meaning the entire visible sphere spans roughly 93 billion light-years across.
Anything farther away than that, we simply can't see it, not because it doesn't exist, but because its light hasn't had enough time to reach us, and never will if expansion continues accelerating. This edge isn't a physical wall or boundary. It's a horizon like the one you see on Earth's surface. Just as you can't see beyond the curve of the Earth from ground level, you can't see past this cosmic horizon.
It's defined by cosmic time and the speed of a light, not by any physical object. What lies at this edge? Not much, just the farthest photons we've been able to detect, the cosmic microwave background, CMB-BB. This faint glow of ancient radiation comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, allowing light to travel freely for the first time. It's essentially the surface of last scattering, the most distant electromagnetic signal we can currently detect. Beyond that, everything is opaque to light. But we know based on models of cosmic inflation and the uniformity of the CMB-B that space doesn't just stop at the observable edge. It keeps going, possibly infinitely. The observable universe is just a small patch of the entire cosmos, the part we're able to access with our instruments and current understanding of physics. The rest remains unobservable, at least for now, and perhaps forever.
What might be out there beyond our cosmic horizon? The best guess, supported by the cosmological principle, is more of the same. Galaxies, stars, clusters, voids, all governed by the same physical laws.
If the universe is homogeneous and isotropic on large scales, as suggest observations, then the regions beyond what we can see probably resemble what we do see. There's no reason to believe we're at a special location. But there are alternative ideas too.
Some physicists have proposed that beyond the observable edge, the universe could become radically different. Different densities, different cosmic histories, even different physical constants. And then there's the possibility of a multiverse.
That our observable universe is just one bubble in a vast cosmic foam of universes, each with its own laws, dimensions, or physical properties. What limits us from seeing farther is cosmic acceleration.
Due to dark energy, the unknown force driving the universe's expansion faster over time, most of the universe is receding from us faster than the speed of light. While that might sound like it breaks relativity, it doesn't.
Because space itself is expanding, not objects moving through space. As a result, many galaxies are already permanently beyond our reach. Their light emitted today will never reach us, no matter how long we wait.
This means the observable universe is shrinking in practical terms, not in size. The radius is still 46.5 billion light-years, but in what we can ever hope to interact with, more galaxies fall beyond our communication horizon every year.
In trillions of years, all but the closest galaxies will have disappeared from view entirely, leaving any future observers stranded in what appears to be an empty, static cosmos. That's the ultimate consequence of accelerated expansion.
Still, within our observable volume, we can study the structure of the universe in incredible detail. We see about 2 trillion galaxies, and thanks to instruments like the James Webb Space Telescope, JWST, we're now detecting galaxies that formed less than 300 million years after the Big Bang, incredibly close to the edge of the visible universe.
And as JWST and future telescopes probe deeper, they give us a clearer picture of what the early cosmos looked like. Star formation, the birth of galaxies, and the buildup of structure that would eventually shape the modern universe.
But even with this detail, there's a hard wall we can't break. We can never observe anything beyond the cosmological horizon, no matter how powerful our telescopes become.
No signal, no matter how energetic, can cross that boundary if it's been stretched beyond reach by space itself. The edge of the observable universe is a limit not just of technology, but of causal fundamentality. It also invites philosophical questions.
If there's more universe beyond what we can see, and all evidence suggests there is, then how much of it is there? Is it infinite? Is it curved or flat on scales we can't probe? Are there versions of us out there in an unimaginably vast multiverse? Or is our universe a one-off anomaly? These are the kinds of questions that push cosmology into the realm of theoretical physics, areas where evidence is scarce, but reason and math offer guidance.
Inflation theory, the idea that the universe underwent a rapid exponential expansion in the first tiny fraction of a second, predicts that the universe could be much larger than what we can see, possibly infinite, possibly curved, possibly connected to other bubble universes.
In some models, inflation never stops entirely, spawning new universes in an eternal cascade, a process known as eternal inflation. But we can't prove it, not yet.
All our evidence comes from what's inside the observable bubble: the galaxies, the cosmic microwave background, the distribution of matter, all of it limited by the light cone that defines our cosmic reach. We can only infer what's outside based on what's inside.
It's a bit like trying to understand the shape of the Earth while standing on a hill and looking to the horizon. You can get clues, but you can't see the whole thing. One final twist.
The boundary of the observable universe is not the same for everyone. An observer in a galaxy billions of light-years away would have a completely different observable volume. Their horizon would include galaxies we can't see and exclude some that we can.
In that sense, there is no single edge of the universe, only personalized horizons defined by location and time. Each observer in the universe has their own observable bubble. In summary, the edge of the observable universe is not a wall, but a limit.
A horizon that marks how far we can see, how far we can measure, and how far we can know. Beyond it lies a realm of unanswered questions. More galaxies, more matter, more space, and possibly much more mystery.
The universe continues past our vision. How far and how strange it gets remains one of the biggest questions in all of science.